Looks like somebody is already here. Wow, the dedication. Thank you so much. Hi, Vizzy. Can you hear me? Let me check on my mobile to see if the sound is okay. Dedication. Thank you so Yeah, much. I can hear it. I can hear it. So yeah, we'll start from. Oh, hi, Pelivan. Okay, I'm sorry for butchering your name. Yeah, that's awesome. Hi. Hope you enjoy the stream. Yeah, I've been having a lot of fun with these live streams. I didn't expect there are so many followers, which is really amazing. So today's idea is to have a linear algebra problem session, as the title suggests. But we're gonna start around 7:20, between 7:20 to 7:30, in about 20 or 30 minutes. And so we're just gonna spend the first part of the stream like chit chatting. Hi Rob, happy Saturday to you too. So yeah, this week has been a really productive week, I've got to say. And by the way, the idea of this live stream actually came from a viewer. So this is my community post tab. Um, so I think let me go find the exact comment, which is I think one of the solutions, or not really solutions, but rather results, the distribution of the scores of one of my quizzes. Sorry, a collection of quizzes. Let me go find it. It's Yeah, it's this one. It's about 4 days ago. Here I posted the results of the second set of 10 quizzes I posted in my community tab. And here you can see how many people responded and what are the average score. And so I got this comment, big streaming. Hi, Peter. So, um, actually, no, not this one. Sorry. Sorry, not this one. Can we go back? Because somebody requested it. And unfortunately, as far as what I can tell, at this moment, I haven't received a follow up from that viewer. So that person requested me to have a problem session, so to say. But I haven't, and he said there's some problems he wished me to go through them for preparing an upcoming exam. I figured why not? So that was the idea, which I responded right away saying I will host a problem session stream, but I haven't yet received the problem sets, but that's okay because I still like the idea. Hey, mate, I'm sending you the problem set right now. I'm not okay, okay, okay. That's great. That's really awesome. Let me okay, because I also prepared my. I mean, not my own, but I found another pretty nice set. Okay, you can send it to my email. By the way, there you can find my email in the about page. It's mathwithming@gmail.com, and I'll take a look. And because yeah, as you can see, it's confirmed on live that I have no prior knowledge about what this problem set is about. So I will see how good or badly I can do. Okay, so no Loomis and Sternberg today, but I hope this is going to be fun. Yeah, so I was talking about this week in 5 minutes. Okay, I'll just keep talking about my week. So this week I managed to upload a few videos, two on stochastic calculus, I said three, all three on stochastic calculus. I've been watching one of your videos recommending statistical inference. Do you think that's the best book to start? The best book to start. It's a strong question. So, that book is meant to be a first introduction to mathematical statistics. Okay. You were talking about the video. I think you're talking about what's it called? A Kasselenberger, which I reference quite a lot. Which Ming has problems with my start program. Thank you so much. Take that as a compliment. So this book, Conquering Mathematical Statistics, with this book, Kasselenberger, right? Statistical Inference by Kasselenberger. How should I put this? I listed all the prerequisites of that book in the video. So if you have that, then I don't see any reason you cannot start with that one. It's not going to be an easy read, okay, but it is designed for a first introduction, and it's very rigorous, modulo measure theory. Okay, so as far as a non-measure theoretic introduction to mathematical statistics is concerned, in my opinion, there's hardly any book can exceed Kasselenberger. It will give you a very solid foundation, in my opinion. Needs prerequisites. So what are the prerequisites? Linear algebra, multivariable calculus, and a first course in probability. Okay, so you need to know what are, for example, joint distributions. What are convergence in distribution, convergence in probability, central limit theorem, that sort of stuff. Okay, and perhaps not at a very advanced level where you can manipulate things at ease, but you need to know those things exist and seeing some common distributions and know how to work with them. So I would say this is at the level of, in terms of North American curriculum, university curriculum, a third or fourth year text. Kasselenberger. I sent you right now. Okay. Thanks, Vizzy. Have you? Yeah. I saw your message from Set. Okay, great. Have English translation too. This is Chinese. Okay. I can do Chinese, but still. This is Japanese. Sorry, this is Japanese. Okay. This is still. Can everybody see the screen? This is Japanese. I never seen math in Japanese before, which is very cool. Okay, so that's the translation, I suppose. Awesome. So the first problem. Here we go. Let me. Okay, I'll use a reference, which is Linear Algebra Done Right by Sheldon Axler. Okay, and this was the original problem set that I prepared. I didn't prepare, I downloaded from the internet, and I figured it's quite good, but we don't need this today. Okay, just purely focus on the questions Vizzy give us. Okay, so the problem one is a linear algebra problem. It's got 3 parts, looks like it has got to do with eigenvalues and stuff, and orthogonal matrices. Okay. And here we have a differential equation problem. Second question is the differential equation problem. So it looks like part 1 to 3 and part 4 to 7 are independent. Okay. And problem 3 is a probability question. Wow. Looks like we're calculating mean variances and some probability bonds. That's cool. So those are the 3 questions. Huh? Okay, great. Let's start with the linear algebra one. And by the way, do you guys want to see like the document after I've done the stream, perhaps? If so, I will. Let me use what's OneNote, right? OneNote. Yeah, I'll put my notes and steps together and compile as a file, upload to a Google Drive, and so you can see. So let's start with linear algebra. That will be better. Okay. So let me start here. I'm still new to this app. Can we add? Yeah, it's a new one. All right, great. So let's start with the problem 1, part 1. Okay, I didn't expect to start this early. I said I'm gonna wait for like 20 minutes or so, but you know what the heck, let's just get started. What's the fun of talking about my week when we can have real problems to solve, right? Problem 1. Let A be a matrix as such. So this is a block diagonal matrix. And the first block looks like it's symmetric. Okay, so that's a nice observation. Find all the eigenvalues of A. For each of these eigenvalues, find a corresponding eigenvector. So this is a very standard problem. So this is problem 1, part 1 is not, I would say, challenging. So this is very mechanical. Let me use the blue color. 1. Oh, this is too sick, huh? I think this is too sick. Can we? Yeah, that would be better. 1. So let's use the standard technique. So first, eigenvalues. Eigenvalues. So we set up the characteristic equation. That's the determinant of A minus lambda I. Okay, equals 0. And because of the block diagonal structure, things can be simplified. Okay, first evaluate the left-hand side, which is called the characteristic polynomial. 5 minus lambda minus 4 minus 4, 5, 0, 0, 0, 0. Oh, sorry, missed a minus lambda here. 16 minus lambda. So use the cofactor expansion from the last row or the last column. We get 16 minus lambda times the determinant of the 2 by 2 matrix. A 2 by 2 matrix in the upper left corner. 5 minus lambda, negative 4, negative 4, 5 minus lambda. And keep expanding. So 16 minus lambda times 5 minus lambda squared, negative 16. Okay, so this is just a straightforward computation. 16 minus lambda times, so 16 is 4 squared. Use the difference in squares, so difference of squares, so it's 1 minus lambda times 9 minus lambda. So these are the eigenvalues, which are all distinct. Lambda 1, let's write it from small to in an increasing order. So to say lambda 1 is 1, lambda 2 is 9, and lambda 3 is 16. Okay, so now let's do the eigenvectors. The eigenvectors. So the eigenvectors are defined as non-zero vectors v such that AV equals lambda v. So for eigenvectors, applying the linear transformation A is equivalent of a scalar multiplication. V is non-zero. Okay, that's an important requirement for the eigenvectors. Otherwise, the equation is trivial. And this is equivalent to A minus lambda I, where I is the identity matrix, V equals 0. So let's just do one eigenvalue at a time. And because these are all distinct eigenvalues, we're guaranteed to have one, just one linearly independent. That's not a rigorous statement. I'm trying to say is because these are all distinct eigenvalues, the eigenspaces corresponding to each eigenvalue has dimension exactly 1. So for lambda 1, a minus lambda 1I is lambda 1 is 4, lambda 1 is 1, sorry. So you get 4 minus 4 minus 4, 4, and 15. So this is the matrix. I'm omitting the zeros. Main question, what if the eigenvalues aren't distinct? What if they have algebraic geometric multiplicity? Very good question. I won't watch it now because it's okay, but I want to express my gratitude. Thank you so much. Thank you, Mixery Asta. Thank you so much. Yeah, you can always catch the recording later. It's from the textbook. Sorry, I'm late. No, it's from a viewer, Vizzy. So Vizzy sent me this problem set. Okay, and it's got 3 problems. Problem 1 is linear algebra. Problem 2 is differential equations. Problem 3 is probability. Okay, so I'll try to solve as many as possible during the stream. That's the idea. Okay, right now I'm at just problem 1, part 1. Okay, it's not from a textbook. It's actually from a Japanese university graduate school entrance exam problem set. So pretty cool. Yeah. Yeah. So actually, I have very little idea about what the culture of mathematical education is like in Japan. We've been doing like Ito's integral and Ito's lemma and stuff, right? So Japanese, they know their stuff. Anyway, so this is the matrix A minus lambda 1I. So to solve this equation right here, this is a homogeneous linear system of equation. So we just need to use the row reduction, which is quite fundamental. So what we do, we can first multiply or divide the third row by 15. So R3 over 15. This turns the last row into 0, 0, 1. And next, we can add the first row to the second. So R2 plus R1. And that just gives us a 0 row. Everything is 0 here. Okay, and we can, and finally, we divide R1 by 4. So 1 minus 1, 0. 0, 0, 0, 0, 0. Okay? So, and then multiply that by a vector v. So a minus lambda 1 I times v, which we assume to have a coordinate form v1, v2, v3 to be 0, is equivalent of v1 minus v2. I'm doing just matrix multiplication. Just read all the coefficients. v1 minus v2 equals 0. And the second equation is just 0 equals 0, so no need to write it. And the last one is v3 equals 0. So v3 is determined. Chapter in span. So this is not the book we were working on. This is a problem set. This is a problem set. From a viewer. Okay, we're doing an eigenvalue problem. All right, so that's the system of equation, and we just need to find a non-zero solution. Right, so in fact, let's find the eigenspace to make things more systematic. So we have v1 equals v2, v3 equals 0. So as in linear algebra, when we reduce our solution to this form, we would pick a free variable. And the convention for doing so is to pick the variable that does not correspond to a pivot column. Column 1 has a pivot, aka leading one. Column 2 has none. Okay, column 3 has a pivot. Therefore, we pick V2 as per our convention. Why did you do the row transformation? Like, yeah, so it's a good question. The idea is to turn the original matrix into a row-reduced echelon form. And why don't we just go back to, go to linear algebra done right. Perhaps this is a little bit advanced for that. I don't know, like, does Shelton-Axler cover REF? Huh, perhaps this is too advanced. Actually, I'm sorry. Let me give you a much more interactive resource. Hang on. It's from my home university, actually. If you guys want, like, just the most standard, okay, no fluff, linear algebra resource, okay, that start from the bottom up. Check this out. Open Math. It's called University of Waterloo Linear Algebra Open Math. So we have this website that has linear algebra 1, linear algebra 2, apply linear algebra 1, apply linear algebra 2. Okay, so unfortunately, as for now, the Open Math project only has linear algebra. Yeah, so just Google Open Math U Waterloo. You will find interactive lessons, quizzes, and so on. For example, if you go to the system of linear equations, I'm pretty sure you can find the lesson on REF. Yeah, LADR almost entirely ignore matrices. So that's not a first introduction, which is not a critique for Axler. Axler assumes you had a more computational course, somewhere in the preface, basically. Anyway, that's not what matters. But here, we're dealing with the fundamentals. So let's go to, for example, here. There's the video here. Let me play that to get an idea.
Gauss-Jordan elimination.
Yeah, this is one of the most amazing instructors I've ever encountered. And here you also have the alternative format, basically in text. So if you don't want to listen to a video, you can go here. So this is the basic idea. We want to reduce a matrix to its row-reduced echelon form. And the row-reduced echelon form has this format. First of all, it has, why he not answer me? Sorry, did I miss your question? JC, hang on. I was just looking at the math. Okay, sorry. Did I? I couldn't find your question. Can you repost it right away? I'll answer it right away. Jigs, if you post your question right now, I'll answer it. Perhaps I missed it. Okay, I was reading the textbook doing math, and perhaps I missed it. Okay, if you can repost the question right now and I'll answer it. Okay, so this is the strategy. For example, we see the first column has a non-zero entry. So we start from this column. We need to make the entry in the first row of this column a leading one. So you want to make 2 a leading one, so you divide that by 2. So every step has its motivation. Okay, I won't read out this example line by line, but I'm pointing out resources. Okay, yes, Gauss-Jordan is the same as row-reduced echelon form. The final result is the REF. Okay, so the final result is REF. So we want to have something like this. The result has this echelon form. So basically, the leading one of the rows that are higher up are to the left of the leading ones that are in the rows below. Okay, and each column that contains a leading one must contain the leading one as its only non-zero. Everything else has to be 0. Okay, so this is really just a way of eliminating variables in high school linear system. Okay, so if you want to solve a linear system in high school, you would try to eliminate variables as much as possible. The Gauss-Jordan format is just a matrix encoding of that process, and it saves you a lot of writing. Okay, so let's go back to our problem here. So we have V1 equals V2, As I said, the second column contains no leading one, and it is our convention that we pick the variable that corresponds to the column with no leading one as the free variable. So v2 is a free variable. This is t, free variable. Okay, I got you. Now let's move on. Let's open math. I study how the algorithm works. Okay, great. Awesome. So let's go. V is v1, v2, v3. So it's t, and 0. So that's the most general form of the eigenvectors for the first eigenvalue. So that's why it's you have this format t times 1, 1, 0. So every eigenvector for lambda 1 is a multiple of 1, 1, 0. Hi Peter, thanks very much. We can write E lambda 1, that's the eigenspace. The eigenspace, which is defined as V such that A minus lambda 1i, V equals 0. So basically that's the solution set of the eigenvector equation. Okay, that's the eigenspace. The eigenspace turns out to be the span of 1, 1, 0. Okay, so it's the line through the origin in R3. Okay, great. Let's move on. And the rest are pretty similar. Okay, A minus lambda 2 I equals what? So you have lambda 2 is 9. So it's minus 4, minus 4, minus 4, minus 4. Okay. 0, 0, 0, 0, and 16. No, not 16, but 16 minus 4. So that's a 12 here. Okay, great. So sometimes I use the square bracket as a notation for matrix. Sometimes I use round bracket. Okay, it might look a little bit confusing. I apologize for that. Now once again, we want a leading one in the third row, so simply divide R3 by 12. And let's do R2 minus R1 to clear out everything in the second row. And lastly, let's do R1 over minus 4 to get a leading one. Okay, so 1, 1, 0, 0, 0, 0, 0, 0, 1, and that's an REF. Okay, and therefore A minus lambda 2i times V equals 0 is equivalent. Once again, I'm taking the coordinate form of V as V1, V2, V3. Lambda 2 is 9, not 4. My is 9? Yeah, oh yeah, it is 9. Sorry, my bad. So the last row becomes, I was really stupid. So last row is 16 minus 9, so it's 7. That's 7, okay. Thankfully, it doesn't cause us real damage, okay. That was my excuse. Eagle eye, thank you so much. Yeah. Yeah, thanks, Clark. Thanks, Clark. Anyway, so here we have V1 plus V2 equals 0, and V3 equals 0, right? Okay, so this means V1 equals minus V2, which is our free variable. V2 equals t, free, and V3 equals 0. Nice. And that's this way we have V, the vector V, to be t minus t actually. V1 is minus V2, t minus t, t and 0. So you end up getting t times minus 1, 1, 0. And the eigenspace for lambda 2, E lambda 2 is the span of there's a question I think I forgot to answer. Is like somebody asked what happened if you have multiplicities, right? Yeah, that's a good question. I think that's the question I forgot to answer. So basically what happens is there's no guarantee that a square matrix would have a full set of eigenvalues as a basis for here, let's say R3. So in that case, if you have a full set of linearly independent eigenvectors for the domain of the linear operator, then the matrix or the linear operator is said to be diagonalizable. Not every matrix is diagonalizable, okay? But if you do, let's say you have a multiplicity in your eigenvalue. Let's say you have lambda 2 equals to 9 as a repeated eigenvalue, okay, with multiplicity 2. It's still possible to have two linearly independent eigenvectors associated with lambda 2. It's still entirely possible. And the process is the same. You still do the same REF business. And if the solution ends up having two free variables, then so be it. Okay? And that's how you tell. There's no special trick to it. If your linear system, say A minus lambda I equals 0, only has a one-dimensional solution set, but the corresponding eigenvalue has a multiplicity of 2, then it just shows that your matrix is not diagonalizable, and this can happen. Okay. Anyway, so here we have the second eigenspace, lambda 3. Let's keep on going. Lambda 3 should be very easy. Lambda 3 should be very easy. So lambda 3 is 16 a minus lambda 3I. So the last row simply becomes the 0 row. Okay. Here 5 minus 16 gives us minus 11. Minus 11, minus 4, minus 4, minus 11, 0, 0. Okay? So actually we can skip the REF business and simply declare that to get, because we can simply get that from inspection, right? So this is, certainly you can do the REF and stuff. That's to get an REF, the row reoperation, you can do that. But simply by inspection, you can observe that the vector 0, 0, 1 is an eigenvector, because that's the definition of eigenvectors, right? So if we have a multiplicity of 2 and 2 free variables, then it will be yes, yes. So in that case, Clark, in that case, we say that the geometric multiplicity is also 2. The geometric multiplicity refers to the dimension of the eigenspace. So if the geometric multiplicity and the algebraic multiplicity are equal for every single eigenvalue, then the matrix is diagonalizable. Okay. And by the way, everything here is in this resource, and is in linear algebra 1 diagonalization. I think I was just quoting the lessons here. Diagonalization theory. Okay. Whenever in doubt, go to this website. You can find quizzes as well. Yeah, let all the distinct eigenvalues of a matrix be lambda 1 to lambda k. A is diagonalizable if and only if G lambda I equals to A lambda I. This is saying geometric multiplicity equals algebraic multiplicity for all the eigenvalues. I just quoted this theorem here. All right, let's keep going. So I was saying by inspection, you can see that 0, 0, 1 is an eigenvector for 16. To see that, let's simply do the matrix multiplication. A times 0, 0, 1 equals 16, 0, 0, 1. That's it. So you can skip the REF. Okay. So by inspection, E lambda 3 is just the span of 0, 0, 1. Okay, so that completes the calculation. So conclusion, Okay, let's make a table. Eigenvalues, eigenvectors. You have 1, 9, 16. For 1, the eigenvalue is 1, 1, 0. For 9, the eigenvalue is minus 1, 1, 0. And the last one is 0, 0, 1. Okay, so the problem is complete, but we're going to do one step further and make a simple plot. Okay, so this step is optional for solving the problem, but I think it's a good practice if we keep doing this, okay, to build up some geometric intuition. So plot. So this is our R3. So here, let's say this is x1, x2, x3, usual coordinate system, and this is our plane, the horizontal plane, x1, x2 plane. Can we do that? Yeah, very nice. So this is our plane, and let's plot all the eigenspaces. E3 is the easiest, it's just the x3 axis. So let me change that to a different color. Can we change that to a different color? Yeah, let's do purple, okay? So this is E3. E lambda 3. Let's just write E16, okay? Because lambda 3 is 16. And for these two, for lambda 1 and 2, they both lie in the x1, x2 plane. So let's make a separate plot that only includes the x1, x2 plane to make things easier. x1, x2. x1, sorry, the E1 is the direction 1, 1, 0, so it goes like this. So that's the line x1 equals x2. And this is E1. The eigenspace for lambda 1 equals to 1. And E2 is the orthogonal direction, minus 1, 1, 0. So this is E9. We can draw these two lines on the 3D plot, like so. So this is E1, and this is E2, okay? And to emphasize that they are orthogonal, let's put that on the plot. Okay, not E2, but E9. I mean E9, not E2. E9 is 9 is the value of the eigenvalue. Okay, and this is actually not a coincidence at all, because the first block, 5 minus 4 minus 4, 5, this is a symmetric matrix. It is guaranteed that a real symmetric matrix would have orthogonal eigenvectors. So it is guaranteed a priori that just by the structure of the matrix being symmetric, we are guaranteed to have its actually all three eigenspaces are mutually orthogonal. So E1, E9, E16 behaves like a coordinate axis, right? Behaves like the orthogonal coordinate axis. And that's the special property of symmetric matrices. And for that, you can go to the open math resource, go to linear algebra 2, where a lot of more things are discussed about orthogonal matrices. So if you go to application orthogonal matrices, think which one? Orthogonal diagonalization. Orthogonal diagonalization, in particular, there's the celebrated principal axis theorem, which can be generalized into a more advanced version called the spectral theorem. The principal axis theorem says that if a matrix is symmetric, then it's orthogonally diagonalizable. It means there exists a set of mutually orthogonal eigenvectors. Okay, so that's guaranteed by this theorem, which we've just seen from this example here. Okay, so that's the first problem. It's quite nice. And by the way, this theorem is hugely important for statistics. This is why you can do things like the principal component analysis. Otherwise, that would not work. So in statistics, the most important symmetric matrix is the covariance matrix. Both the theoretical covariance matrix of a joint distribution and the empirical covariance matrix for a random sample. Okay, it's because of this linear algebra fact that we can perform statistical analysis such as the principal component analysis (PCA) by doing this, because of this theorem. And it's also important in classical mechanics, quantum mechanics, and so on. But for quantum mechanics, you need complex matrices. Okay, but I digress. Let's go to the second question. Actually, find a real symmetric positive definite matrix B that satisfies this property, B squared equals A. So we're trying to find a square root of the matrix A, right? Okay, so that's part 2, based on our result in part 1. So how do we even approach this problem? Let's just do the draft here. Can we do that here? Do I have... Okay, let's still do it in our notes, not in the PDF reader. So how do we approach this problem? Well, what we just did is we diagonalized A, right? We just diagonalized A. So what do we have so far? From part 1, we found a set of eigenvectors for A. So let's put P to be let's put P to be our orthogonal matrix, an orthogonal matrix that whose columns form an orthonormal basis. So let P be my V1, actually V1 over V1 norm. Okay. So this way, the vector, this is, what's that called, V1? Okay, V1, V9, and V16. I'm going to normalize these vectors so that I get an orthonormal basis. Orthonormal bases are applied mathematician's dream because they're so nice to work with. So let's just get that matrix first. First, we are not going to work out the details, but we know this exists. Okay, this is an orthogonal matrix, 3 by 3 orthogonal matrix. Beautiful matrix. Okay, and because of these are eigenvalues, sorry, these are eigenvectors, what we have is A times P equals to big lambda P. And what is this? This is nothing but a matrix version of the definition of the eigenvectors, AV equals to lambda V. So let me just show where does this come from. As I just said, the columns of P are all eigenvectors and they're mutually orthogonal, right? So we have A V1 hat, this stands for normalized V1, AV1, lambda 1, V1 hat, A V2 hat equals lambda 2. So this is part of the theory, okay? You don't typically write this in your steps when you submit the solution, but this is just the theory. I mean, I figured why not we review it a little bit, right? So this is all true for all 3 normalized eigenvectors. We can put this into a matrix form. So let's put the first column of the matrix on the left hand side to be AV1 hat. That's the first column. Okay, that's the first column. And then AV2 hat and AV3 hat, like so. Okay, and on the right hand side you have lambda 1 V1 hat. This is nothing but just a reorganization of these 3 identities into one matrix equation. Okay, like so. Lambda 3 V3 hat. But what is the left hand side? The left hand side is simply A times v1 hat, v2 hat, and v3 hat. So that's AP. Okay? And on the right, we can interpret as a matrix multiplication as well. And this is how it works. So you create a diagonal matrix, lambda 1, lambda 2, lambda 3. And then you have v1 hat, v2 hat, v3 hat. Let's check this works. So you can think of this as row times column, the usual way you do matrix multiplication. Lambda v. Hang on, is this right? This doesn't feel right, huh? Actually, this is wrong. I'm glad I checked this because this feels wrong. This should be like this. Diagonalization. This should be p times lambda, huh? I think it should be p times lambda. Yeah, otherwise the block multiplication makes no sense. I'm glad that I checked this. Because if I just go with this one, then this is actually wrong. Okay, I'll fix that in a second. But just to see how this actually works, so this p times lambda, not lambda times p. If we do the block multiplication, you can treat v1 hat as a scalar and just do the usual block multiplication. v1 hat times lambda 1, v2 hat times 0 plus v3 hat times 0, which gives you exactly lambda 1 times v1 hat. That's what you want. Okay, am I going over this too fast? Okay, let me summarize. We have these eigenvectors, eigenvalues, eigenvector, eigenvalue, and eigenvectors from part 1. And now we can organize our result in this format. AP equals P lambda, where P is an orthogonal matrix whose columns are normalized eigenvectors. And be sure to keep track of the order we're looking at. No, it's fine. Excellent. And lambda here is the diagonal matrix of eigenvalues. And I was trying to say that be sure to match the indices of the eigenvectors and eigenvalues. So, for example, if the first column of P is V1 normalized, then the first entry, the first diagonal entry of lambda must be lambda 1. Okay, great. Awesome. So we just verified that this identity holds because I wasn't sure and I wrote lambda p and it turns out that it should be p lambda. That's why we always verify because I don't do this every day. I mean, so yeah, I'm making excuses for myself. But yeah, this is the identity readily obtained from just the previous calculation. And what else? How can we work with that? There's a theorem which says if P is orthogonal, then the inverse matrix of P is just P transpose. I want to know the thought process. Yes. Where are we finding the orthogonal in order to solve this problem? Yes, here it comes. Here it comes. Here it comes. This is called Cholesky's factorization, actually. Well, how do we approach this process? I'm telling you right now. Okay. A equals b squared. A equals b squared. So we have this form for A, right? So, I mean, we just have this form for A. We can express A in terms of a factorization. Let's multiply P transpose on both sides. Let's right multiply P transpose on both sides. This is I. So A has this format. A has this format. Okay, and why do we want this? Because lambda has an easy square root. Lambda is a diagonal matrix whose diagonal entries are 1, 9, 16. Diagonal matrices are very easy to raise to a power and take square root of. Okay, so what we can do is we're going to rewrite this as, let's write lambda, square root of lambda, to be the square root of lambda 1, the square root of lambda 2, and the square root of lambda 3. And it's a trivial matter to check that the square of this matrix, this is just a notation, square root of lambda, which means this. You can check this, the square root of lambda times the square root of lambda is lambda. Diagonal matrices are really easy to take square root of. And we can define our B to be P lambda, the P times the square root of the lambda times P transpose. And let's calculate what's B squared. What B squared is. B squared is P square root of lambda times P transpose times P square root of lambda P transpose. P transpose P is I, property of orthogonal matrix, and lambda square root times lambda square root gives you lambda back, which is P lambda P transpose equals A. Congratulations, you just found B. And there's an extra component, extra requirement in the question that you want a real symmetric positive definite matrix. Right? You want a real symmetric positive definite matrix. This process guarantees B is symmetric. Let's check B is symmetric. B transpose equals P square root of lambda P transpose, use the property of the transpose. You would reverse the order in the product. So P transpose gives you P, the square root of lambda transpose, but square root of lambda is symmetric, so that's just square root of lambda itself times P transpose. So it's P square root of lambda P transpose, which is exactly B itself. So B transpose is B, is symmetric. And B is also positive definite. Why? The definition, actually one of the definitions of positive definiteness is all eigenvalues are positive. Okay, that's one way to define positive definiteness. Another way is to use quadratic form, but we're not going to bother with that here. Because by this very formula of B, the eigenvalues of B are square root of lambda 1, square root of lambda 2, square root of lambda 3, which are positive. So that's it. Square root of lambda i's are positive. So all the requirements are done. And now it's just a matter of calculating this formula. Question: in practice, do we encounter matrix power in any real world? Absolutely. Absolutely. Matrix powers are everywhere. So a classic example would be the Fibonacci sequence. Let's go to Axler. I remember very clearly, Axler put the Fibonacci sequence right on the very first page or something. This is calculated using matrix power. Okay, I'm just going to leave that as a homework. You can go check it out. How do you, this is Fibonacci sequence, by the way. Everybody knows about Fibonacci sequence. F of n plus 2 equals fm plus 1 plus fn. Okay, and then how do we find the general formula for fn? Well, let's define a vector, say x. xn is fm plus 1 and fn. Okay, so this is our vector, and by this definition, xm plus 1 is f of m plus 2 fm plus 1. Okay, so xm plus 1, you can write it as fm plus 2, so that's fm plus 1 plus fn plus 1. And you can write it as a matrix multiplication, which is fm plus 1, fn. And this is 1, 1, 1, 0. So this is xn on the right-hand side. So you have xn plus 1 equals to a constant matrix times xn. So therefore xn is just this constant matrix. Let's just call it a raised to the n x naught. And then you extract the component you want. You get this formula. Okay, so matrix multiplications, matrix powers are supremely important for difference equation, which is used for modeling discrete time dynamical systems. Okay, anyway, so back to this question. We did some theory crafting here, right? But if you know this by heart, then you would just need to calculate this equation. That's it. Okay, but the problem, the calculation itself is rather straightforward, so I'll just list the formula, if that's okay. So P, let's do the normalization. V1 hat is, this is V1 hat, V2 hat, and V3 hat. This is orthogonal matrix. V3 hat is the easiest because this is already a unit vector. 0, 0, 1, right here. V1 and V2 both has a norm of square root of 2. So it's 1 over the root of 2, vector divided by its own length, minus 1 over square root of 2, 1 over the square root of 2, 0, 0. So this is P. And you can calculate P transpose, which I'll not write. Okay, and lambda is 1, 9, 16. So the square root of lambda, as per our theory, is 1, 3, 4. Square root of 9, square root of 1, square root of 9, square root of 16. A positive square root to ensure positive definiteness. This ensures positive definiteness of B. The eigenvalues of B are 1, 3, 4. Okay, and actually, what can we say about this expression? What are the eigenvectors? The eigenvectors are the same, right? Because if A has this form, right? A has this form, A right here, it tells you that the columns of P are the eigenvectors, the diagonals of lambda are the eigenvalues, and take a look. B must have the same eigenvectors, and the square roots of the eigenvalues of A are the square roots, sorry, not the square root, but the eigenvalues of B. So you get the eigenvalues, sorry, the eigenvectors for B as well, for free. So therefore B equals, as we just said, P times the square root of lambda. P transpose satisfies 1 B squared equals A. The calculations are omitted, calculation details are omitted. Part 2 is B symmetric, and 3, B is positive definite. Philosophy log says, I have a question about covariance matrices. Why is it that given a Gaussian covariance matrix of dimension plus 2 plus, we could quickly sketch a contour by passing the vector onto sigma t? By what do you mean by passing any vector onto? So maybe this is a trick I've never heard of. Okay, maybe this is a trick I never heard of, but usually when you see a covariance matrix, recently come across, I found it relevant when you come across finding a matrix of recent problem. Can you send me a link? Anyway, it doesn't have to be right now, but yeah, I'll take a look at it. So what you usually do when you plot the contour, so to say, of a quadratic form, because quadratic form and symmetric matrices are in one-to-one correspondence, you can sketch quadratic form by finding its eigenvalues and eigenvectors. Right? So essentially, the eigenvalues decides the axis length, the major and minor axes of, say, an ellipse, or it could be a hyperbola, right? Depending on the values, depending on the sign of the eigenvalues. Okay. So here we have, because in our problem, because this is positive definite matrix, the contours are ellipses. The contours for the quadratic forms are ellipses. Okay, I'm going over this super fast, okay, because it's not what the question asked for. And it's all in here. And then you rotate the axis according to the eigenvector directions. So this is a slanted ellipse. And this is what we usually do when we, say, plot the contours of a bivariate Gaussian. Because the bivariate Gaussian has a covariance matrix that is a 2 by 2 matrix, symmetric positive definite, and it's guaranteed to be symmetric positive definite. Otherwise, the integral would blow up, right? The normalization condition for the probability distribution would not be satisfied, right? So it's guaranteed to be positive definite. So don't worry about like plotting a hyperbola or something. This will never happen. But in theory, you can do this for all quadratic forms. Okay. Yeah, send me the link. Perhaps this is a shortcut that you just mentioned, which I have no idea of. Okay. I love to learn from my viewers. Actually, I learned a whole lot. And many have pointed out mistakes in my videos, which are, embarrassing, but still important. Okay. This is what I try to foster on the channel. Don't just watch mathematics, do mathematics. Anyway, so I think we're done with question 1. Question 1, part 1, which has 2 subparts. Okay. Part 2, let's go. Part 2 looks like a proof question. Perhaps this sort of question requires more thought process behind them, right? Because when we did part 1, the first question, finding eigenvalues and eigenvectors, is strictly mechanical. It's just a fixed procedure. Part 2 requires a bit of a knowledge of how to factorize a matrix based on the results of diagonalization. Once you have a matrix factorization, taking the square root is easy. Now, does the diagonalizability of matrices like this come from spectral theorem? Absolutely. Absolutely. Because the matrix A is symmetric, then by the principal axis theorem, which I just listed, which I just showed in the open math, it is guaranteed to be orthogonally diagonalizable. Can you explain your thought process for the second question? Yes, I'm getting into it. You mean the thought process of this one? I wrote here. I wrote it here. So you do need to kind of know this before. If you never see matrix factorization, it's kind of difficult to think about it on the spot, if that makes sense. Okay. Anyway, so yeah, so part 2, let C be a real symmetric positive definite matrix. Okay. Show that there exists a unique satisfying. We just did the proof here. This is the proof. You just do it for n dimension. I want to understand your reasoning. Yes, absolutely. Like if I just write this and I don't show this, this feels like magic, right? If I don't show the purple part, even instead I just, write b equals to p squared of lambda p transpose, boom, done. That's not very enlightening, right? The magic comes from the spectral theorem, essentially. Orthogonal diagonalizability. Because the question did not raise that specific knowledge, then if you have never seen this, it's kind of hard to think about it, to think of this trick on the spot. But we just proved, essentially, right here. But to put it in a formal proof, let's respect the norm of proof writing. Hello, is there or are there plans to cover a Discord server for this channel? It might be nice. That would be amazing. That would be amazing. Damn, I should really do that, huh? Or actually, is it easier to do? I've seen other YouTubers having a community where other people can post on your channel. Do you guys think that would be a good idea? Because not everybody has a Discord server, right? My demographics are, I would say, a little bit older than the YouTube average. If we can just stick everything to one platform, would that be easier? Anyway, we'll figure this out. Okay, the channel logistics. Let's not distract the math. Yeah, create a Discord server. Okay, we'll do both, I guess. We'll do both for sure. I have Discord. Anyway, so let's see be a real symmetric positive definite matrix. Let's write the proof. Respecting the format of proof writing. Discord is a lot easier to discuss problems. For sure. Yeah, I guess so. I guess I'll have like a math with Ming, a math stacks exchange, something like that, right? So, apologies for distraction. No, don't apologize. This is a fantastic suggestion. Okay, so how do we show existence in general? This is standard proof writing technique. Okay, the question asks us to show existence. There are two ways to show existence overall. The most dominant method is to actually give an example of how to construct such an object. So this is like a constructive proof. And this, we have the perfect candidate for that right here, this formula. And we just need to justify why p and lambda exist in general, which we just mentioned is the principal axis theorem, right? And so that's the first approach, the constructive approach. So we're 100% sure that this question can be done using a constructive approach, namely give a procedure, if not an explicit formula, of the thing that we need to show exists. Okay, so that's the first approach. The second approach is for proving existence in general would be a contradiction. You assume that the thing that needs to exist does not, and there's a contradiction that follows. So that's the second approach. So overall, showing existence is these two methods. And the overwhelming majority you would see, existence proof you would see are of the first kind, which makes existence proof typically harder than other sorts of proof, because you actually need to do some scratch work like we did here to figure out the form or the algorithm that guarantees existence, right? So that's a lot of scratch work going on at the back. And after the scratch work is done, like we did here, the actual proof itself is just a verification. So when we write this proof, we simply write, okay, let D be whatever, be blah, blah, blah. You give the format, you give the formula, you give the algorithm for constructing D, and then you check D is real symmetric positive definite, satisfy D squared equals C. So this is just a completely backward process. You figure out D, you figure out how do you construct D on your scratch work, and then in a real proof, that the proof that you actually submit to your professor, to the journal that you aim to publish, is just a verification. So it looks very mechanical and unmotivated. That's why proof writing can sometimes appear mysterious, because a lot of the scratch work is not shown in the actual proof. Now, if you read baby rooting, that's kind of one of the biggest issues beginners have. They have no idea how to choose an epsilon, choose a delta for a given epsilon. It's all done kind of in the back of a scratch paper. Anyway, so here, let's start by we want to give this formula, right? But first we need to justify why p exists, lambda exists, and why square root of lambda is a well-defined operation. Okay, so since C is a real symmetric PD matrix, by the principal axis theorem, it is orthogonally diagonalizable. So when we do proof, we don't just deduce, we quote theorems, quote definitions. Okay, C is orthogonally diagonalizable. Okay, so I'm using a lot of, as you can see, shortcuts here. Make sure you write the full letters in your own native language in the actual proof. Okay, so this is C is orthogonally diagonalizable, i.e., there exists a orthogonal matrix P. Actually, here in the question, it did not say the dimension or the size of the matrix, right? So let's actually put that here, just to be unambiguous. Suppose C is m by n. Okay. C is m by n. Okay. Suppose, and so here the orthogonal matrix P is also m by n. This way there's no confusion. So you know the orthogonal matrix is of the same size as C. exists n by n orthogonal matrix P and m by n diagonal matrix P. So actually, you know what? Let's first not use the positive definite part, because this principal axis theorem only needs real and symmetric matrix. It does not need the positive definite part. Okay, so let's write it this way. Let's use the exact hypothesis of the theorem. And exists an n by n diagonal matrix lambda such that big lambda such that what we have, A equals to P lambda P transpose. That's the theorem, what the theorem guarantees. So this is what's doing the heavy lifting here. You don't need to show this as a standard result. You can just quote it. And then next step, since C is positive definite, okay, also given, since P is positive definite, what is the term positive definite mean? Very good question. Let's review. That's the whole point of doing exercises, is to find out the weak points in our knowledge. Positive definite. Do we have symmetric matrices? Where do we define that? I guess one drawback of this format, online format, is that it lacks an index. If you have a traditional textbook, then we'll have index at the back, right? So if you see terms like positive definite, you can use index to find out. Here I have to use my own knowledge to figure out where things are most likely located. Okay, let's go and find the definition for positive definiteness. I mean, it is perhaps more time-saving for me to give the definition right away, but that's not a culture I'm trying to foster, right? So I'm trying to like force you to go to the primary source. Okay, where's the definition of positive definite? Come on, positive. Okay, not here. Definitely in this chapter. Maximum and minimizing, perhaps. Sorry, is that the same page I just gave? Positive definite. Perhaps it's in earlier lessons, huh? You're in linear algebra section. Yes, yes. I mean, I can. Okay, I will not waste any more time. So, definition. This I'm pretty sure you can wiki it, okay, or in whatever text that you use in your university. Positive definite matrix D, symmetric positive definite matrix. This means definition. There are two versions. Definition 1. D is PD. Okay, positive definite if the function x transpose dx is strictly greater than 0 if x is non-zero. That's the definition of the. Actually, if we write this more in a more detailed way, it's greater or equal to 0 for all x, for all vector x. For all vector x in Rn, okay? Let D be m by n. Suppose D is m by n. So for all vector x in Rn, x transpose dx is greater or equal to 0. And there's an extra condition, and x transpose dx equals 0 if and only if x is 0. So the left-hand side can only attain 0 if x is a 0 vector. And when x is 0, obviously, trivially, the left-hand side is 0. Positive definiteness just says this is the only possibility for it to be 0. What is x? X is a vector. I said x is in Rn. Okay, so let me give a concrete example. Let's say you have, why don't we just use the example here? X is a vector in R3. X is a vector in R3. What is X here? So for example, A is PD. A is PD. A is PD. So by using our definition 1, it means the vector X, okay, perhaps I put a vector notation, this way is easier. Vector X transpose A times X is greater or equal to 0 for all X in R3. Okay? And this left-hand side is called a quadratic form. The quadratic form equals 0 if and only if X is 0, the 0 vector. Okay? How do I know that? How do I know that? Well, let's see why this is true. Okay, let's see why this is true. Because this is true, because to see why. Okay, let's see why. Let X be an arbitrary vector in R3. Let X be an arbitrary vector in R3. Once again, we're going to make use of an orthogonal matrix P. Okay, an orthogonal matrix P. P is orthogonal, and therefore P is invertible. Orthogonal matrices are automatically invertible. Let X in R3. Define Y such that X is Py. This Y must exist because P is invertible. So we're defining Y as a solution of a linear system, of equation. Py equals X. Or you can simply write equivalently, or equivalently, define Y to be P transpose X. This is an explicit formula. That also works. Okay? Because P transpose is just P inverse. Define Y to be this. So what about X transpose AX? What does that look like? Hi, cat. X transpose is Y transpose P times, Y transpose P transpose A times X. X is what? X is, well, Py. But what is this sandwich in the middle? P transpose AP. That's big lambda. We had this factorization here. Right? We had this factorization. AP is P lambda. Right? Which gives this form, but you can also multiply P transpose on both sides and get P transpose A. P equals P transpose P lambda. P transpose P is identity. So this is I. So this is lambda. So therefore P transpose AP is lambda. And we have the quadratic form equals to Y transpose lambda Y. Let's spell this out in coordinates form. Y transpose is a 3 vector with coordinate y1, y2, y3. Okay? And lambda is what? Lambda is diagonal matrix 1, 9, 16. 1, 9, 16, this way. And y is y1, y2, y3, column vector. Expand everything out using matrix multiplication, you get y1 squared plus 9y2 squared plus 16y3 squared. Can we see why this is always greater or equal to 0? This is a sum of squares. And the fact that the eigenvalues are strictly positive plays the crucial role here. If let's say you have a negative number in these 3 numbers, then it is not guaranteed to be non-negative anymore. Right? And this is positive definite. We also need to verify, to show this is also positive definite, we need to show the last condition as well. So basically, if this is, the quadratic form is 0, it must mean that X is 0. How do we show that? How do we show that? Well, here we have this identity. X transpose A, X, the quadratic form is y1 squared plus 9y2 squared plus 16y3 squared. This can only be 0 if all the y components are 0. And if all the y components are 0, py is 0, so x is 0. So these two are equivalent. And in this little derivation, what we managed to show is something quite important. That is the second definition of positive definiteness. Positive definiteness. Sorry, English is not my first language. So sometimes I stutter. Definition 2, D is PD if all eigenvalues of D are strictly positive. So immediately from the calculation where we have 1, 9, 16 as the eigenvalues, we can immediately conclude that the matrix in part 1 is positive definite. Okay? And actually, when we write definition 2, there is another theorem going on in the background. We just said all eigenvalues are positive, right? All the eigenvalues are positive. This sentence can only make sense if all the eigenvalues are real. Remember, we cannot compare complex numbers. If eigenvalues, which can totally be complex in theory, right? Even if you have just a real matrix, you can still have complex eigenvalues. So when we write this definition 2, we already are assuming a fact that the eigenvalues of D are real. And that's actually guaranteed. You don't need to worry. You don't need to worry about complex eigenvalues here because it is a proposition, it is a property that symmetric matrices must have real eigenvalues. Symmetric matrices must have real eigenvalues. That's a theorem. So here, when you write definition 2, there's no danger here. P is symmetric, D is symmetric, then we're guaranteed that the eigenvalues of D are all real. So you can say whether they're positive or negative. All right? Okay, that's definition 2, positive definite. So we're doing the original proof. Since C is PD, the diagonal, the eigenvalues, all the eigenvalues lambda 1 all the way to lambda n. I'm not claiming that these are distinct, okay? So these are counting multiplicity, to be precise. Counting multiplicity, there must be n eigenvalues. What do we mean by counting multiplicity? Let's say if lambda equals 2 is a repeated root with algebraic multiplicity 2. So imagine when you factorize your characteristic polynomial, you end up with a mouse doesn't work very well. A minus lambda I. Imagine you have a factor that looks like lambda minus 2 squared with some other factors. Then when we list this, when we list this list of eigenvalues, 2 would appear twice. So this is what we mean by counting multiplicity. Okay, let me erase that. So all the eigenvalues are positive. Right. This is by definition of positive definiteness, by definition of PD matrices. So this is this gold standard of writing proofs. You do deductions and you list the justification. The first step 1, the justification is the principal axis theorem. The second justification is the definition of PD matrix. Okay, so now let's do the construction of D. Define D. So now we have the ingredients. We can cook the D up. I proved the rage on one node. Thank you very much.
So let's define D to be, what's our formula here? Is P times the square root of lambda times P transpose. P square root of lambda P transpose, where the square root of lambda is defined as the diagonal matrix square root of lambda 1 all the way to square root of lambda n, right? Where square root of lambda I denotes the positive square root of lambda I. This is well defined because all the lambda i's are positive. So you see, one step is built on the previous one. Okay, so now let's verify a few things. So first, let's do the algebra. D squared equals to C. D squared is P square root of lambda P transpose times P square root of lambda. This is essentially what we just did. Okay. First, collapse the middle term. P square root of lambda square root of lambda P transpose, since P is orthogonal. Okay, P is orthogonal, and thus P transpose P is I. Okay, and then P times lambda, because square root of lambda times square root of lambda is just lambda. Okay, and this is A. So this is verified. 2. Well, P is a real symmetric matrix. D is real and symmetric matrix. Real symmetric. The real part is easy because D is real since the matrices P square root of lambda are real. So their multiplication must be a real matrix. Are real. Okay? And let's verify that D transpose equals to D. This is very mechanical. D transpose is P square root of lambda P transpose. We also did that earlier. Because lambda is diagonal matrix, so it's symmetric. Square root of lambda is diagonal matrix, therefore it's symmetric. And this is just D, same as D. Okay, that's done. D is PD, since square root of lambda i's are eigenvalues of D, and they are all positive. And QED. Right, that completes the proof. So this is the existence proof, right? So when we do existence proof, this is the crucial point where, so when you declare something exists, you need to define it and justify why this operation is valid always. Okay, here the existence of P and lambda are justified by the principal axis theorem. The positive definite part indicates all the eigenvalues are positive, so the square root of lambda is well defined, and the rest is just verifications. Okay, I think we're done with this question. This is much harder if we do not assume real from the problem statement. Do not assume real. So let's say if C is a complex matrix, but for complex matrix, the symmetric counterpart would be so-called Hermitian matrix. So essentially, the conjugate transpose of C equals C, in which case you still have the analog of principal axis theorem. So for Hermitian matrices, the eigenvalues are also real. So the square root of lambda is still well defined. But the the eigenvectors are no longer real. Remember learning about Hermitian matrices, but haven't studied much complex. Actually, you know what? Go to the website, open math, right after applications of orthogonal matrices, you have complex vector spaces. Okay? Right. So it runs very much in parallel with the study of symmetric matrices in real, which in my opinion is actually a waste. It's pedagogical inefficiency because the complex vector spaces completely subsumes the theory about real symmetric matrices. Actually, doing proofs in a complex vector space is easier because even for real matrices, you have to worry about complex eigenvalues anyway, right? So this is another instance which I wrote in my post. I recently made an announcement about the upcoming complex analysis course, right? So you guys have seen that. I got tons of likes. Thank you so much. I think this is the most like I've ever got from a post. I wrote at the very end, complex numbers in a sense are easy. Now when you're doing algebra, complex numbers are easy. The reals are nasty. And the same is true for analysis. Historically, complex analysis matured much earlier than real analysis, even though they started out as a single subject. Right. So anyway, I'm really looking forward to this one. And the first video is going to be like a trailer. Okay, the first video is not going to be definition of complex number. Nobody will watch that, let's be honest. Everybody knows what definition of complex number is. If I just start lesson 1 with the definition of complex number, nobody would be interested in the series. Right? So the first episode is going to be a historical one, and it's going to be very exciting. So stay tuned for that. Anyway, let's get back to linear algebra. We've done part 2. Let's do part 3. So part 3 is another 3-part question, 3 sub-part question. Let's do that. Okay. I'm doing this full proof. By the way, this is what I would personally write on an exam. I'm doing this full proof to standardize the steps of proof writing. Okay, the reasoning behind it, as well as the standard of writing. Okay, this way, not only you have an idea of how a proof works, but also communicate that idea properly to the standard of mathematical communication. So part 3, let a real square matrix F be non-singular. So what do we mean by non-singular? Actually, you know what? Let's start carefully. Let's from this point on. Okay, whenever I go over a question, I will define the terms. How about that? Non-singular just means invertible. It's the same word. Okay, it's the same meaning. Non-singular just means invertible, and invertible matrices has a bunch of characterizations, such as determinant non-zero, having full ranks, and so on. Okay, which I will not go over individually. And by the way, let's go back to the open math, linear algebra 1, invertible matrices, inverses, invertible matrices. There's at least 7 or 8 characterizations of inverse matrices. Matrix inverse. So there's something. I think it's here perhaps. Matrix inverse. Yeah. Now, just as a review, I think it's a very good exercise if you manage to prove all of this. Inverse matrix theorem. You have that. Yeah, inverse matrix theorem. Invertible matrix theorem. Exactly 8 equivalent conditions. Right. So exercise strongly recommended. Do that. Okay. It's a very good way to practice definition. Invertible matrix and non-singular matrix are the same thing. So go to this section on inverse matrices, prove the invertible matrix theorem. It's a good way to practice definitions. Anyway, get back to the question. Let's show that there exists unique. Wow, not only existence but also uniqueness. There exists unique real symmetric positive definite matrices S and T, and unique orthogonal matrices U and V satisfying SU equals F equals VT. This is interesting. So here we have just an invertible matrix F and nothing else, right? And we need to show there exists unique symmetric positive definite matrices S and T. So S and T are, we want, this is our scratch work. What do we want? We want S and T, which are PD. Okay. And by the way, the notion of positive definiteness only describes symmetric matrices. So yeah, if you say something is positive definite, the matrix is positive definite, it's already implied that it is symmetric. And unique orthogonal matrices, U and V are orthogonal, such that SU equals VT. SU equals VT, and they are equal to, and they equal F. So how do we approach that? Let's think about, for example, the first identity. F goes SU, right? So we want this. We want this to be true. And U is orthogonal. So let's do some shenanigans about our goal. Let's multiply U transpose on the right. So this way, so FU transpose is UU transpose, which is just S. So what does this say? This says that a symmetric positive definite matrix is in the form of an orthogonal matrix times an invertible matrix. I don't recall a theorem that looks like that. I don't recall a theorem that looks like that at all. So that's not very productive. That's not very productive. So why don't we reverse the logic? Let's suppose now I have positive definite matrix S, and I'm going to orthogonal diagonalize it and see what happens. So suppose now S is given, and it's real symmetric positive definite, okay, just PD. S is given as PD. And we know from the principal axis theorem we can orthogonally diagonalize S. So S equals, what's that form? A equals to P lambda P transpose. So S equals P lambda P transpose. Lambda P transpose. So we can do that for sure. How do we cook this up? We want to multiply S by another orthogonal matrix U. So why don't we just let U to be P? This way S times U is S times P. Okay, I'm just exploring things. Okay, S times U equals S times P, which is P times lambda. Remember, P transpose times P is identity. Right? So what does this say? What is P times lambda? What is P times lambda? We want P times lambda to be an invertible matrix. Remember, P times lambda is a special form, right? P times lambda, right here. P times lambda is a special form. So P times lambda is a special form. That's just the columns of Let's just, what is this thinking called? What is this thinking called? I'm reverse engineering, basically, right? Because I have a hard time trying to think of how to construct these matrices. I'm now flipping the logic. In the question f is given, right? In the question f is given, we want to show that there exists S and T U V blah blah blah. I'm now in the exploration, I'm now reversing the logic. Suppose that S is given. Can I cook up a relation that looks like F equals to SU? That's the thought process. Okay, so here I write S. Suppose now S is given. Suppose now S is given. Can I write S times U equals to an arbitrary non-singular matrix? And then I'm going to write the proof backward. Did I answer the question? Okay, so where was I? So okay, I understand. So anyway, this is S, and I pick U to be P, and I pick U to be P, right? And I wrote SU equals P lambda. SU equals P lambda. SU equals P lambda. So something, I want this to be an arbitrary symmetric matrix. I want this to be F. F is just an arbitrary invertible matrix. I want this to be F. But the problem with this approach is that P lambda has a special structure. Remember, P lambda has this special structure. Lambda is diagonal, P is orthogonal. So P lambda looks like lambda 1v1, lambda 1v1 hat, lambda 2v2 hat, and so on. And therefore, by this format, the columns are all orthogonal, because the P's has orthogonal columns. P times lambda is just each row of P gets scaled by the eigenvalue. And scalar multiplication does not alter orthogonality. So here, this is still not okay. This does not work, because by this construction, P lambda has orthogonal columns, which is not guaranteed for arbitrary invertible matrices. So this is not okay. So this does not work. Okay, we failed once again. So this time I suppose S is given, but I still couldn't cook up the result. So why don't we use something else? Let's try singular value decomposition, SVD. Let's go to linear algebra 2. SVD, which is the last section of the second chapter. So there we go. SVD. SVD is nice because it is guaranteed to exist. Right? For any arbitrary matrix, not even square ones, rectangular ones too, have SVD. Definition: a singular value decomposition of an m by m matrix A is a factorization of form. By the way, if you're watching it on mobile, the text might be a bit small. Let me do this. Okay. The definition of SVD. So here you have a rectangular matrix A m by n. This is not necessarily a square matrix, and it has this form. So the sigma is a semi-diagonal matrix. It's not a standard term, by the way. The only non-zeros in big sigma are the diagonal ones. The entries with identical indices, identical row and column indices. Okay, sigma looks like this, and it has the same size as A. Almost diagonal. Okay, as diagonal as it can be. If A is not a square matrix, sigma is as diagonal as it can be. And U and V are orthogonal matrices. Okay, U and V are orthogonal matrices, but there is actually, this is just a definition. I'm talking about the theorem. The theorem says SVD always exists. The theorem says SVD always exists, but it's not here. It always should always exist. Huh? Yeah, but it's not explicitly stated in these notes. But the process of constructing the SVD always works. So it's implicit in this algorithm here to find an SVD. You can always do this. You can always do this for arbitrary matrix. So I'm just going to take that as a theorem, okay? For any arbitrary matrix A, you can factorize this way. However, nothing is said about uniqueness. Bro, about to pull out of Gram-Schmidt. Oh, never mind. Gram-Schmidt. Actually, you know what? Gram-Schmidt. Oh, if this idea fail, we'll try Gram-Schmidt. How about that? Because if you're talking about Gram-Schmidt, then the idea is here you have non-singular matrices. So non-singular matrices, the columns forms a basis, and then you can orthogonalize it, right? You can use Gram-Schmidt and construct an orthogonal basis. But the problem is it's not unique, right? Isn't the orthogonal matrix is formed by the Gram-Schmidt is not unique, right? So anyway, we'll get to that. But if I'm not dismissing that idea at all, okay, I'm not dismissing that idea. I'm just still trying to follow the line of thought of SVD. So let's say if we use SVD F, okay, F equals to U sigma V transpose, where U and V are both orthogonal. Okay, and sigma is the singular value, or the singular values, and singular values are always guaranteed to be non-negative. Singular values are always guaranteed to be non-negative because singular values are. Let's go back to the notes. The singular values sigma I are the square root of the eigenvalues of A transpose A. A transpose A is always positive semi-definite. So A transpose A is always have non-negative eigenvalues. So little sigmas are always greater or equal to 0. Anyway, so what can we do with that? How can we cook up SU and VT here? How can we cook that up? If let's say we let U to be V transpose, what is U times sigma? Is that a symmetric positive definite matrix? Ah, okay, I know what to do now. This shenanigan. This is the shenanigan here. U sigma U transpose, that's our S. I tried working ahead and wondering you kind of, yeah, it works. This is what we wanted. So existence is now shown. Vizzy, did you get what I mean? I'm going to use a trick. I put a U transpose U in between sigma and V transpose. The first three matrices together forms a positive symmetric definite matrix. I'm not sure about the definite part, but at least this is semi-definite. Actually, it should be definite. It should be definite because if it has a 0 eigenvalue, then F would be singular. So that's another information. So F singular is now used. Okay, and orthogonal matrix, because here U and V transpose are both orthogonal matrices. Orthogonal matrix times an orthogonal matrix is still orthogonal matrix. So this is S times U. This is what we wanted. And you can use a similar trick to get the VT part. Okay, so after doing SVD, you get what is that? So you get V transpose sigma. Sorry, not V transpose. V sigma V transpose, this is our T, and V transpose here, U here, this is your V. F equals SU times VT. We're done. So it's just a manipulation. Yes, yes. I mean, you have to explore options, like we did earlier, right? If you just seen the proof, let's say, of this construction in the final answer, it feels rather mysterious, right? But this is usually how it works in the background. You use trial and error. You try to explore as many options as you can, right? So we failed a bunch of times, but now I think we got it. But this is only the existence part. This is only the existence part. We need to show uniqueness as well, right? We need to show uniqueness. But anyway, actually, you know what? This is what I would recommend instead. Okay, in our attempt, we try to show existence first and uniqueness second. All right, I need to feed my cat real quick. As you can probably hear some cat noise in the background. 2 minutes, okay? Why did you do that trick? Well, it takes experience, right? It's just plain and simple. You can go back to the recording. I had some previous attempt, which is not written here. I erased them and I explained why they failed. Right? I tried SVD as like a final resort, as a last resort, because I know F can always has an SVD, right? And SVD has something to do with symmetric matrices and orthogonal matrices, right? So that's kind of the logic here. I mean, I don't have a better explanation other than, I'm just trying to explore options. So you need to, I guess you have to have a good foundation, right, to naturally connect those ideas. That's, I guess, part of the challenge of learning math, right? Anyway, let me just go feed my cat real quick. She's going crazy. Hey, I'm back. Yeah, anyway, so that's the scratch work. But we also need to show uniqueness. So if a question asks for showing something unique exists, then that proof must have two parts. Existence proof and uniqueness proof, done separately in almost every circumstance. Okay? And it is a general pattern. Okay, I wouldn't say this is true for every theorem. Uniqueness is easier. Existence is hard. Okay, so uniqueness, what really uniqueness says is there is at most one set of objects that satisfies blah blah blah. This is what uniqueness means. Okay, existence means there's at least one such object. Uniqueness says there's at most, and you combine them together. Okay, so uniqueness, in the discussion of uniqueness, you don't even need to assume existence, which makes uniqueness proofs, generally speaking, easier than existence proof. Think about all the mental gymnastics we just did, right? This trick out of nowhere, U transpose U, we have to come up with to do existence. For uniqueness, you just need to suppose there are two sets of such quantities that we wish to show exist, and then deduce they are the same. Okay, so let's do the uniqueness part first. I think that's more natural. I mean, if you actively develop that habit when seeing exam questions, because in exam questions often, let's say all your attempts fail, then what do? You don't write a whole single word. That's not a very efficient strategy for getting marks, right? Uniqueness is easier to show. So if you struggle with struggle with existence, forget about it. Do the uniqueness part first. Okay, so I'm going to follow that advice and do the uniqueness part first. Because uniqueness has a very how should I put this? It's a very standard format. Let's do uniqueness. Okay, so we're going to suppose we have real symmetric PD matrices S1, T1, S2, T2, and orthogonal matrices U1, V1, U2, V2, right? Such that F equals S1, U1 equals V1, T1, SU, VT, okay? That's you can think about it this way. So this is the first group of objects. And this is equal to S2, U2, V2, T2, second group. This is our assumption. And we need to show that. To first set up our goal, we need to show S1 equals S2, U1, S1 equals S2, T1 equals T2, U1 equals U2, and V1 equals V2. Okay? Uniqueness. This is uniqueness. So let's actually go about doing that. So what can we say? Why uniqueness? So I guess it just boils down to manipulating these equations, which there are a few, so which I guess it can take a while. So why don't we start with some scratch work on the side? Let's say you have S1 U1 equals S2 U2, right? And this is equal to F. So perhaps let's do, in exams there's a time constraint, but the thing is I can't generate too quickly. This takes a lot of time. Exactly. Yeah, this is the math. I mean, it's not just math, right? It's also the time constraint. So it's not easy. I'm not trying to make the case that okay, you can just naturally, but you know what? This is but I'm trying to like give as many marks. This is like the marks maximization strategy, so to say. You can set up the proof. No, this is uniqueness proof. This is very standard. So existence proof takes tricks, right? Uniqueness proof is very straightforward. Actually, you know what? If you find part 1 is too hard, assume part 1 and see if you can do part 2, part 3. Okay. Anyway, let's do the what's that? S1 equals S2. How do we do that? How do we show uniqueness? Because there's a lot of variables. How can we pin down S1? Because let's say if S1 equals S2, if S1 equals S2, then U1 should equal to U2 automatically, right? Hmm. How can we show uniqueness? I just said uniqueness tends to be easier, but I'm still struggling, you know. Anyway, I bit my own tongue. How can we find uniqueness? There's so many matrices. Which one should we start with first? U1 and U2. Maybe U1 and U2? Well, how do we just construct it U? So this is kind of cheating because we're using the construction. Usually when you do uniqueness proof, you don't use the construction. But anyway, we were here, so let's try that. So because our U is, it's not obvious from this formula because SVD, even though it's guaranteed to exist for every matrix, is not unique. Okay, so here U and V are not guaranteed to be unique. So why U times V transpose is unique, right? It's not clear. So it turns out that the construction is not very useful for uniqueness. We have to work from these hypotheses. My goodness. S1 U1 equals S2 U2. How do we get to, say, one matrix being equal? I think the logical step would be showing S1 equals S2. Because if you have that, then U1 and U2 being orthogonal matrices must be equal, right? I can't convince myself at this moment, but let's just try to figure out why S1 and S2. Focus on S1 and S2 first. Is it possible to try F transpose and write at an expansion for, actually, you know what? Let's try that. F transpose. Or perhaps F transpose F? Because F transpose S feels more natural, no? F transpose F. Okay. Let's try that. Because when you do SVD, you diagonalize S transpose F. F transpose F. So let's use, let's say, S1 U1 as the first F. Okay, transpose. S2 U2. So we get U1 transpose. U1 transpose equals S1 transpose S2 U2. Proofs can be frustrating sometimes. Yeah, it is. It can be. It can be. Yeah. That's why I'm trying to create a low-stake environment on the channel. You do the quizzes, and so you try to develop a database, so to say, of those easily missed topics. And this way, I mean, just like learning a language, the only way to improve is to accumulate, right? So, especially for high stress environments like entrance exam. So, I don't know what else I can tell you. Is everybody suffers the same pain in their journey in mathematics. But it can be rewarding. I'm just trying to put some silver lining on top of it. Anyway, F transpose F, what do we want to do with that? Write an expression of S in terms of F. Because the problem with that is S is the problem with okay, so S1, first of all, S1 from here, S1 is F times U1 transpose. F, yeah, this is transpose. So can we say this is S2? This is the first thing I tried, no? U2, F1, I put F1 as S2, U2, U1 transpose. What else can we do here? Existence proof is done. That's usually the harder part. How are we stuck here? I'm still here, by the way. I'm just thinking. Let's say f is s times u, and also f is v times t. What's the relation between s and t then? What's the relation between s and t? Can we do that? Perhaps this step might be standard, but it's difficult to work with. There's too many equations here, right? So let's explore the relation between s and t a little bit. I might have to erase this, okay? But anyway, I think this setup is, even though it's standard, it's not working right now. But f is s times u. Okay, I want purple for scratch work. F is s times u, and also f is v times t. So can we write t in terms of s? Say t is, let's multiply v transpose on both sides, so v transpose s times u. This is f. What is f inverse, so to say? What's f inverse? F is non-singular, right? We haven't used that condition. So let's try f inverse. F inverse is by the identity on inverse, SU inverse is V inverse times S inverse. V inverse is V transpose. Oh, sorry, U transpose because U is orthogonal. S inverse. This is F inverse, okay? F inverse. So, and also by the second relation, F equals to Vt, F inverse can be written as T is T inverse V inverse. So this is T inverse times V transpose. Can we connect that to what we have here? I want a relation between S and T. There should be a relation between them, right? A more explicit relation. I know SU equals VT, right? So can we express S in terms of T and F? I don't want the U's here. So let's look at, I want to keep S in the middle intact. Here I have a U. Here I have a U, and I want to get rid of that. F is SU. F is SU. I want the S, but I don't want the U. So can we do S inverse SU this way? This is F, no? S times U. But here, I don't want that. This is odd. I want a relation between S, U, and F. I don't want the intermediate matrices. Is it possible? So our goal is to find a relation between F, S, and T. That's it. I don't want UV to appear in the relation. F is SU equals VT. F inverse is what? F inverse we just said is UT. S inverse equals to T inverse V inverse, which is V transpose. So if let's multiply T on both sides. Can we do that? And what is FT? I'm just exploring options once again. What is FT? FT is SUT, right? FT is SUT. Yeah, I'm thinking if you can, let's say, write S and T in terms of the, can write S and T in terms of the matrices. So you show that it satisfies this relation. Oh no, this is my friend. Anyway, if we look at part two, if S and T satisfy this relation, T equals F inverse times SF, and U equals V. What do if we have that, can we show does part 2 and 3 helps with part 1? Sometimes it does, because questions sometimes they mess with you. If we have part 2 and 3, does that help with uniqueness? Sorry, did somebody say something in the chat? If we try to prove SU equals I, F transpose, sorry, philosolog, F transpose is because U is orthogonal, S is symmetric, U and V are orthogonal, S and T are PD. Yeah, you're right. We managed to show existence, but why uniqueness is turns out to be harder. Huh? S and T in question satisfy T equals. I was also trying F inverse, but then substituting, but I think it becomes a tautology I equals I. Actually, does it have to do with perhaps? Does it have to do with the previous part? Could it be? Could it be has to do with the previous part? It's not obvious, right? Are these questions supposed to be independent, or it doesn't say, right? It just struck me that perhaps part 2 is useful. We use SVD to show existence. Can we use, say, part 2? I mean, this certainly works, and I don't want to erase that. So perhaps let's try let's try the result from part two. So part two says if you have a real symmetric positive definite matrix, then it has a unique positive square root. Oh no, I didn't show uniqueness in part two. I screwed up. You see, I totally missed this key word here. So okay, um, guys, I'm so sorry. Yeah, use part two. I'm so sorry. Yeah, perhaps this is something we also need to, because I've never done an exam for years. This is standard exam cramming. I mean, with no. I mean, this is of course. I'm just kidding. Okay. It doesn't matter if you're doing exam or studying mathematics on it for its own sake. Always try to use the most immediate result that you just got. I mean, I totally forgot that. Okay. You know what? Let's finish up the uniqueness proof for part two, and then try part three later. Okay? Because this has been kicking our butt. My butt. Okay, not you guys. But anyway, I'm trying to finish up part two because I certainly missed the uniqueness part. That's not good. Uniqueness. How do we show uniqueness? Because we just constructed D in this manner. How do we show uniqueness? Okay. Yeah, we'll come back to part three shortly, okay, after we finish up uniqueness. Because the uniqueness part might be useful for the uniqueness part in part three. Existence. Okay. Uniqueness. So how do we do uniqueness here? So let's suppose you have D1 and D2. Suppose you have D1 and D2 that are real, symmetric, positive definite, such that D1 squared equals D2 squared equals P. Is that P or C? I think C, right? That's the notation in the question. And then we need to show you need D1 equals D2. Whenever a problem kicks my butt, I skip the problem and go to the next problem and come back to the problem and kick my butt again. Somehow it gets solved. Yeah, it happens. It happens. I feel you, man. It just happened to me. Well, I'm not sure about the problem being solved later part, but let's hope for the best. All right, we need to show D1 equals D2. How do we show D1 equals D2? Does a matrix, I mean, I'm obviously trying to do this, but is that true though? I think generally you cannot do that, no? Because this requires the commutativity. So yeah, this requires commutativity. So this is not okay. This is this. How do we show that the square root is unique? Okay. So the difference in square formula does not work for matrices. No, I mean, I wouldn't call myself very smart. I guess, average intelligence. I mean, but the thing is, I do consistently do math, but hopefully we get to resolve this issue. So how do we show D1 equals D2? We have D1 and D2, both are the square roots. And we constructed D in the manner of eigenvalue decomposition. And by the way, my idea was was that, or do they commute, right? Do D1 and D2 commute? Because they have this property that their square equals to C. Let's try on the side, okay? Let's see if D1 and D2 would commute here. D1 D1 times D2. No, it's not obvious that it would commute. So what about, let's say you have D1 equals D1 square equals C. D2 square also equals C. Again, we're stuck. Again, this is really hard. Okay, so anyway, but can we assume the uniqueness part in part 2 and do the uniqueness part in part 1 and in part 3.1? So if we use part 2, we need a symmetric positive definite matrix. Right? F here is only non-singular. So you got to work with, I guess, F transpose F to get that. You need to work with F transpose F, I suppose, to get the S and T. And by the way, this is called polar decomposition. I know such thing exists, but I never proved it myself. You can go check out Sheldon Axler's book, I guess. It's called polar decomposition. It looks like this matrix, by the way, this looks like the complex number z equals r times e to the I theta. R is positive, and theta is theta, e to the theta I, e to the I theta works like a rotation, right? So u is an orthogonal. So this is called polar decomposition. So I would recommend read polar decomposition. Read about polar decomposition, okay? I mean, of course, if you don't know this term, then it's unlikely you know what to look for. But I mean, I know such thing exists, but I never worked through Sheldon Axler in full detail. So it would be a good opportunity to check that. So we have, it's called polar decomposition. I'm pretty sure it's called polar decomposition. Do we, it's, let's go to the index, polar decomposition. I know this is cheating. Okay, this is not allowed at all in exams, but I guess we're all trying to learn. Polar, do we have polar? Yeah, polar decomposition. I know this topic exists in the book, but I never tried it. Says, okay, just brief notation here. So suppose you have an operator, just think about this as a square matrix. LV is just a linear map from V to V. Okay. And we have, there was polar decomposition too. Yeah, I'll read polar decomposition. And then you have, exists a unitary operator, S unitary operator. So unitary operator, you can think of it as a generalization of orthogonal matrix, okay, for complex case, such that T equals S times the square root of, you see it has to do with square root. So So you have to use part 2. T star t. Has to use square root. Has to use square root. Okay. So, and the polar decomposition below is valid on both real and complex inner product. Okay, so that's the proposition here for polar decomposition. So this kind of looks like our problem, right? So S is orthogonal, so that's VT here. T is positive definite, right? So the T in the question is played by the square root of T transpose T. And this S, the unitary operator, plays the role of V. So that's the existence shown by square root. So it definitely has to do with part 2 and not SVD. Because using SVD, even though it works, it feels like starting from scratch, right? Anyway, that's the polar decomposition. But this is only existence. There's no uniqueness in this proposition yet. Let's go back to a little bit earlier. Polar decomposition. Recall discussion before blah blah blah. The analogy between complex number z with z modulus equals 1 and the unitary operators. Right? They're both rotations. Complex number is rotation on the plane, and the unitary operators are rotations in, well, vector spaces, complex vector spaces, complex inner product spaces. Continuing with this analogy, note that every complex number can be written in this form. Yeah, this is the polar decomposition for a complex number. Our analogy leads us to guess that every operator t can be written in a unitary operator times this. That guess is indeed correct. So in our case, it would be the square root of f transpose f. F transpose f. And what would be the that's the angular part. F transpose, the square root of f transpose f, that would be the angular part. No. That's like the radius. No, that's like the radius. This is the radius of the complex number. Yeah. And T transpose T star T, this is a complex transpose, is a positive operator. Positive operator. Why positive? Does this mean invertible? What does LV mean? Is it all the linear maps or invertible maps? Let's go to the notation. Is there a notation part for the book? LV. Does LV means invertible transform? LV notation symbols. Yeah, LV 52. It's just a linear map, LV. It does not mean invertible linear maps. Huh. All right. To singular route decomposition. It's a consequence of SVD, I guess. SVD for linear maps and matrices. 258, 280, 285. Right here. Is there a uniqueness? No. I mean, it doesn't say. It doesn't say, but it should be unique, even though it's not in Axler's book. So we're pretty sure that to do part 3, we need to use part 2. So we're pretty sure we need to do that. Actually, you know what? Let's erase this part, because I'm pretty sure we need to start over even though the the scratch work here is still valuable, right? How do we start from part two? How do we start from part two and then prove part three? Well, the existence proof, I guess, what would happen if it wasn't unique? It should be. It asks us to do that, but that's not very good thinking. Just because somebody told you that it is unique. What would happen if it's not unique? Good question. I mean, if it's not unique, then something really weird would happen, right? Because the analogy between complex numbers breaks down. If you have a complex number, you should have a uniquely defined unit number, unit complex number, e to the I theta, and the length. We assume it's not unique. We assume it's not unique by doing a contradiction. Yes, that was essentially that was the idea, right? I assume there are two set of such objects, and try to deduce they are the same, right? That's essentially proved by contradiction. So, um, do we have the uniqueness of square roots in Axler's book? Because we were stuck there too, right? In part two, there was a proof for the uniqueness of the square root. 253. Let's go there. Every positive operator only has one, yeah, so that's the uniqueness. How can we do that? Every positive operator on V has a unique positive square root. Okay, suppose you have a positive operator. And by the way, the definition of positive operator, let's go over that first. Positive operator. Positive operator definition. Yeah, so this is called positive. In equivalent matrix form would be V. By the way, section 7 is this real? Oh, okay, it can be real and complex. So it will be V transpose T transpose V greater or equal to 0 in matrix form. It will be this way. Okay, it does not assume definiteness, you see? It's only greater or equal to 0. It didn't say if this is 0, then V must be 0. It doesn't say. Okay, that's okay. But let's go to the proof for the uniqueness of square root. Each positive operator has only one positive square root. Right? And the formal statement is essentially the same. Every positive operator on V has a unique positive square root. And by the way, I usually stop at 10, but today we'll make an exception. I can do a little bit longer. I can stay until I can stay for another an hour and a half. A positive operator can have infinitely many square root. What? Although only one can be positive. Right. That makes sense. If, let's say, we pick negative square roots in the diagonal matrix here, then we still satisfy d squared equals a, but this would not be a positive matrix, right? So, yeah, it certainly makes sense, but here it says a positive operator has a unique positive square root. Right? In part two, we assume that d is positive definite. Anyway, where does the uniqueness part establish? So first of all, assume this is positive. Suppose V is an eigenvector. Okay, it started with from an eigenvector. Then there exists a non-negative eigenvalue. Yes, this makes sense. Let R be a positive square root of t. Okay, so this means we're assuming existence, and that's okay. We have shown existence. We will prove that RV equals lambda V. This will imply that the behavior, we'll prove that RV equals square root of lambda V. This will imply that the behavior of R on the eigenvectors of T is uniquely determined. That's certainly true. right? That's certainly true because the lambdas are all eigenvalues of t. These aren't ambiguous. And here this is actually very smart because if let's say an operator acts on a fixed set of vectors, okay, acts on a fixed set of vectors, they have, sorry, what I'm trying to say is, how do I prove an operator or a matrix is unique, right? You think of it as a linear transformation. A linear transformation is determined by its behavior of acting on a basis, right? Right. Um, if such behavior is unique, that means for any arbitrary vector, because you can, for any arbitrary vector you can do basis expansion, right? So that's the idea. Because there's a basis of V consisting of eigenvectors will imply that R is uniquely determined. And it all just boils down to proving that RV equals lambda V. So that's pretty smart. So this avoids the awkwardness of having to trying to manipulate d1 squared equals d2 squared. Okay, so yeah, let's read that proof and write our own in our own language. Sometimes that's how we learn. Okay, so let's prove that RV equals square root of lambda V. Note that by the spectral theorem asserts that there exists an orthonormal basis of V consisting of eigenvectors. Sure. Because R is a positive operator, all its eigenvalues are non-negative. Therefore, there must exist. Hang on. Why is that? Its eigenvalues are non-negative. Okay. What is E? E's are orthonormal bases of V. Orthonormal bases are consisting of eigenvectors of lambda, of R, yeah, of R. What does this statement say? E1 all the way to En are orthonormal bases, and they are eigenvectors of R. So RE1 is the eigenvalue times E1, no? The eigenvalue of R is the eigenvalue of the eigenvalue of t taking square root. Is that? Hang on. Because R is a positive operator, all of its eigenvalues are non-negative. This is true. Thus, there exist non-negative numbers. Oh, so these numbers aren't necessarily eigenvalues of t, no? It didn't say. Random question, but you have looked into geometric algebra. No, I don't really care about geometric algebra. I don't feel the need for it, to be honest. I think tensors and differential forms do just fine. I know there are proponents of geometric algebra, especially on the internet, that say, okay, this will solve all the confusions in math and physics, but I just don't buy it. Okay, personal opinion, very opinionated, okay, I'm sorry. But I didn't feel the particular need to look into it, and I have competing interests, let's be honest. So that's why I didn't really look into it. I didn't feel the superiority of the formalism, but it has its community. Okay, I never looked into it. I think tensors and differential forms already handle things pretty well. Okay, so what are these lambdas? It didn't say these are eigenvalues of t, even though they should be, no? I guess Axler is just writing the eigenvalues of R as this square root of lambda. Right? So Axler simply denoted the eigenvalues of R as square root of lambda, which is okay. And then you do the basic expansion. So yeah, this is just applying R to V using the basic expansion. And hence lambda V. What is lambda here? Is to prove that lambda is okay. So lambda is taken as an eigenvalue of t. So sometimes it makes it hard to understand something. So, yeah, this is something I say on the channel in the previous live stream. The best textbook is the one that you write yourself. This is the way. I mean, they do it in Harvard 55. They use Axler's book, by the way, in Harvard 55, in Harvard Math 55. But still, every student are required to write their own notes or textbook, basically, in a way that clicks to you. Yeah. So I mean, of course, we're very thankful that these amazing authors like Axler put out their own understanding. But to internalize the material, it's better to write your own. Like even after reading this stuff, let's write your own. So perhaps you can put the intuition on the side, right? Sometimes the authors do that, sometimes don't. But anyway, I'm just trying to follow the proof so we can write our own. Here we have the lambda. By the way, there's no a priori reason that the lambda 1s and lambda n has any connection with the lambda at the beginning, okay? The lambda at the beginning is defined as an eigenvalue of t. So lambda v equals tv, that's the definition for eigenvalue of t. And we assume that r is the square root, so t is r squared v. Okay, so t is r squared v. And then why is this true then? Why is this true? Well, it's because r squared v is r times rv, right? Rv, we use this relation, so it's ra1, let's use the summation notation. Okay, r times the sum I, ai, square root of lambda I, ei. And let's move the r inside, so it becomes the sum of ai, square root of lambda I, riei. Oh, so not r, just rei. And rei is lambda I square root times ei. So the two square roots combine and you have just the sum of ai, lambda I, ei. So this step makes sense now. And now you have two equalities. Hang on. They look the same, no? The above equation implies what? Okay, so here we're doing a basic expansion on the left-hand side as well. So you see on the left-hand side, all the lambdas are the same. And by the uniqueness of basic expansion, a1 lambda is a1 lambda 1. An lambda is an lambda. So therefore we have ak times lambda minus lambda k equals 0 for each k. Does that mean all the lambda k's are the same now? Does that mean all the lambda k's are the same now? Hence, why is v is the sum of k? Hang on. V is a1 e1 plus all the way to an en. This is v. V is okay. So because this is the sum of ak, okay, ak ek, okay, ak ek, and the k here ranges from 1 to n, but we know that for all the k's from 1 to n, this is true. But what if ak is 0 then? What if ak is 0? Then you don't have lambda minus lambda k equals 0. What's v here? V is an arbitrary vector. V is an arbitrary vector in big V. Because um, where's little v? V is, oh, V is an eigenvector. V is an I forgot that. V is an eigenvector of t. So yeah, you see, lambda v equals tv, so it's assumed that v is an eigenvector of t. This weird notation here. AK may be 0. Yeah, that's what I was thinking. AK might be 0. So why can you say that lambda is always lambda k then? Okay, so we do have a1 lambda 1. Maybe because a1 all the way to a1 can be, a can be 0. But this is true for all the a's, right? So that's another constraint, I think. A1, no, A is not arbitrary. A is because V is not an arbitrary vector. V is an eigenvector. My goodness, this is mind-blowingly complicated. I don't know, man. This is sus. AK might be 0. What is V here? This is sus. Okay. Okay. You know what? I think we did enough linear algebra this evening, and why don't we just move on to the next question? Because I don't want to cover kind of everything in the problem set. Okay. My apologies, Vizzy. We will follow up on this for sure. Perhaps or even earlier. We don't have to wait until the next live stream to figure that out. We can communicate through emails and whatnot to figure out some of the. But I'm just pointing out directions. Okay, so for part 3, try to finish the part in Axler about polar decomposition. And I'm pretty sure polar decomposition is not like a standard topic in most linear algebra class. So if you know that, then it certainly would help with that question. But I don't think I'll be able to finish up part 3 this evening. Yeah, move to the next part. Part 2, problem 2. This is a DE question. Let x be a real independent variable, y of x be a real valued function, consider the following ODE. A, B, C are real valued constants. And you have the denominator not 0. Okay, that's assumed. Answer the following questions. Okay, so we're going to first look at some special cases, I suppose, and then we're doing a general ODE problem. For this problem, I think you can make a Discord server. Yeah, make a Discord server. I will. And I'll announce it on the channel. All right. All right, so this is the DE question. Start from part 1. AC are both 0. So AC are both 0, so you got dy over dx. Y plus b, x plus d. Like this. Find the general solution. A equals 0, C equals 0. So this is This is what we call a linear equation, right? This is a linear equation. Because y and dy over dx are both first order. Because c equals 0, so there's no nonlinearity in y. The d is linear. So you can use integrating factor. Let's write that up. Can you separate variables though? You can. You can't separate variables. It's separable. Linear, separable too. Let's use separable method, okay? So this becomes dy over y plus b dx over x plus d. Actually, before the live stream, I made a quiz on stochastic calculus. Can you do this for stochastic differential equations? Turns out you cannot. Because that's what we call an application of the chain rule, which is not true in stochastic calculus, but I digressed. And then you integrate both sides. Okay, so therefore you get the natural log of y plus b absolute value equals the natural log of x plus d absolute value plus constant of integration. But usually we would like to write this as an explicit formula whenever possible, and I think I can. Let's exponentiate both sides. So y plus b absolute value is x plus d absolute value times let's say it's like e to the constant, right? So it's another constant times a constant. And then get rid of the absolute value sign. You can absorb the different signs in the absolute value of x plus d into the constant. So this way we can just write y equals cx plus d minus b. Right? I'm lucky as I can avoid stochastic processes in my work and just use Markov modeling. My condolences, we have to work with stochastic PDE. Yeah, you're a physicist, Sha, I suppose. Are you a physicist? Yeah. So I mean, I guess you're talking about working with Master's equation and Fokker-Planck equation, Kolmogorov backwards forward equation, and so on. Right. But sometimes you have to work with martingales, which are not necessarily Markov. But anyway, so there you go. So that's the first question. It's always a good idea to verify independently. Just substitute into the D and verify, which I'll not do here. C, assume that AC is 1. Convert into a separable form with appropriate change of variables. How do we do that? AC is equal to 1. If A and C times A times C equals 1. So you have dy over dx equals ax plus y plus b over x plus cy plus d. So AC is 1. AC is 1. So let's write c equals 1 over a. We have dy over dx. We need to introduce a change of variable. So that this becomes a separable solution, separable DE. Let's try c equal, yeah, I mean, that's not, we don't need to try, it's just c is just 1 over a. 1 over a times y plus d. Okay? So the obvious choice is to treat ax plus y as a new variable, as a new dependent variable. So let y, ax plus y to be u. Okay, this way you have u plus b, and at the bottom is u over a plus d. Just want to pop in and say I appreciate your Ito calculus series so far. Thank you very much. Thank you very much. Actually, speaking of which, we're here. We just finished Ito's lemma on the series. We're going to take a little break and finish some immediate financial applications. Okay, I know some of the applied mathematics course like to stretch out things a little bit. They cover all the fundamentals and then applications. But I think on YouTube, perhaps that's not the best format because right now the episodes I can already see a dip in views. Perhaps people need time to catch up, right? Which is totally normal. If you know Ito's lemma, you can already do a lot of stuff. So I'm going to pause on the theoretical part of the series. Okay, I'm not going to move into Feynman-Koch next week. So we can actually do some financial stuff already, if that's something that you're interested. Okay. Anyway, so here we have continue on with the d. So u plus b over u over a plus d. Okay, that's the right hand side. What about the left hand side? Well, y is u minus ax, right? Y is u minus ax. So dy over dx is du dx minus a. So left hand side you have du dx over du dx minus a. And I'm pretty sure this is already separable because the right hand side only depends on u. This is what we call, this is what we call a, what's the word? Autonomous d. The derivative is solely determined by the value in the dependent variable. So this is equal to a plus, let's multiply a on both sides, on both top and bottom. So it's a times u plus b, u plus ad. Okay, so factor out the a. Can we do that? I'm pretty sure we can do that. A times 2u plus ad plus b over u plus ad. Yeah. And then you just integrate that. And then you just integrate that. D is not assumed to be 0. Actually, we don't know. We don't know if D is 0. So anyway, this is already separable. And then it's just a factor, a matter of integration. So we have a 2u plus 2ad, sorry, 2u, I'm trying to separate variables, so this is 1 over a times u plus ad on top over 2u plus ad plus b du equals dx. Actually, why don't we just keep a on the right side? Right, so now the integration should be elementary, but you do need to consider cases. AD plus B equals 0 versus AD plus B not 0, I think. But either way, integrating a fraction is simple. Okay, so I just leave it here because I want to cover as much ground as possible. 3. Assume AC is non-zero. Convert it into a homogeneous form. So what do we mean by homogeneous form? A homogeneous form is dy over dx equals a function of y over x. I think that's what it means by a homogeneous form. And of course, here y and x don't have to be the original variables. They can be transformed variables. I guess that's the whole point of the question. And on the right-hand side, what matters is that the right-hand side depends on y and x only through their ratio. Okay, so we want to do something like that. Here, we're assuming AC to be not 1. So this is, I guess, the most general form on the right-hand side possible. And so why don't we just call upstairs the new variable, and upstairs and downstairs a new variable? Can we do that? Let's call the upstairs the new x. Let's call it xi, and the downstairs as eta. Okay, can we do that? I think that should work. I think that should work, huh? Because on the left-hand side, we still need something like this. I think it should work. Let's try this out, okay? Let's try this out. I'm pretty sure I've seen this in some textbook, like years ago, transforming this form into a homogeneous form, but I don't recall the details. Okay, ax plus y plus b and x plus cy plus d, right? So that's the original form. We're going to let the new variables xi equals to upstairs. Actually, you know what? Let xi to be downstairs. Xi to be ax plus cy plus d. And eta to be upstairs. This is ax plus y plus b. Okay, we wish to come up with an expression of dy dx. Okay, we wish to come up with an expression because the right hand side now is just eta over xi. So we need dy over dx. Let's do how do we do dy over dx? Well, dy over dx, you need to use some sort of chain rule, right? We can take the formal differential on both sides. Is that a good idea? Is it a good idea to write dxi equals to dx plus c dy, d eta equals a dx plus dy, and then you solve for dx and dy symbolically, treat it as if this is a linear system. Dx dy, if we, let's say, you can write it as a matrix form, I suppose. D eta d xi is 1 c, this is c. I want to put dy on top, dx at the bottom, so this way it looks like the derivative. C1 dy dx and 1a. Okay, this way there's the condition AC non-zero, A times C non-zero ensures that the matrix is not singular. Okay, so here we have the inverse matrix dy dx, dy dx, the vector dy dx being the inverse of C1 1a, and then we're going to use the 2 by 2 matrix inverse formula. d eta d xi. Okay. All right, so this is 1 over Ca minus 1, 1 over the determinant, and you got the diagonal elements reversed, AC like so, and the off-diagonal elements with opposite sign like so, d eta d xi. All right, so here we would end up with dy over dx equals 1 over Ca minus 1, a d xi minus, a d eta minus d xi, minus d eta plus c d xi, plus c d xi. Okay? And then we just put that into a derivative, and this is 1 over Ca minus 1, Ca minus 1, and you have a d eta d xi minus 1 plus c d, I'm dividing by d xi on both sides, okay? So this is minus d eta over d xi plus c. This is what we got, okay? So this is the left-hand side of the dE, and therefore this thing right here is eta over xi. And then you can just solve for d eta over d xi to get the homogeneous form. And that's pretty much it. Okay. So yeah, and the rest is just high school algebra. A d eta over d xi minus 1 equals Ca minus 1 times eta over xi times minus d eta over d xi plus c. This is significantly easier than the linear algebra question, huh? But just be careful with the manipulation. A plus Ca minus 1 eta times xi. That's the combined coefficient of the derivative d xi over d eta over d xi. Right, change of variable done. And on the right hand side, you got Ca minus 1 times c eta over xi eta over xi, and then plus 1. So therefore, that's the homogeneous form. D eta over d xi equals Ca minus 1 c eta over xi plus 1 over a plus Ca minus 1 eta over xi. And on the right hand side, this is a function of eta over xi only. Right, this is a homogeneous form. And once you have a homogeneous form, you can convert this into a separable dE. We only need to convert it, into a homogeneous form. And by the way, what I was talking about, how to convert this into a separable dE, you just let y over x be u, okay? And this way, the right-hand side is f of u, and dy over dx becomes d over dx of u times x. Use the product rule, you get du over dx times x, and then plus u times 1, okay, just u. Okay, so that's the left hand side, therefore you have du over dx times x plus u equals f of u. Remember, y over x is defined as u, so therefore du over dx is f of u minus u over x, and this is separable because du over f of u minus u, this is standard theory, dx over x, and then you can integrate both sides. So it means once everything is in a homogeneous form, you can convert this into a separable equation. Okay, so there's a nice progression going on in this question. All right, so we've done that part. Let's continue. This is called a Riccardi equation. This has a name for that, called a Riccardi equation. If you guys heard of that, Riccardi equation is useful in control theory. And by the way, how do you check how many people are watching in the stream without going to my phone? I'm such a noob when it comes to streaming stuff. That's 13 people. That's not too bad. My goodness. Thanks for sticking around. All right. Yeah, this has been a bit quiet in chat. Does the first question in D make sense to you? Does part 1 make sense? Vizzy, you still here? This is for you, man. And for everybody else, right? We're having fun. So, yeah, so that's the first question. And the second question is this is a Riccardi equation. What I was talking about. So go read that in Wikipedia or something. This is one of the challenge in the 17th century, because the Riccardi equation in general does not have closed form solution, as it turns out. And mathematicians during that time were trying to, the primary research direction, I would say, during 17th and early 18th century was to solve differential equations using integrals. Right? But it turns out that, of course, such methods are highly restricted. Right? And Riccardi equation was one of the first that challenged a lot of mathematicians at the time, Euler, Leibniz, and whatever, couldn't solve it. So it prompted a more qualitative theory, because calculus was pushed to its limits. Anyway, I digress. So now let's consider a ODE of the following form. P, Q, R are real value functions dependent only on x. Sounds good. The key here is that you have both linear and nonlinear terms. If you have both linear and nonlinear terms, things get tricky. And also there's the constant term. Px is considered as a constant because it does not depend on y. Right? So there are some special cases we're going to cover first. Assuming r is 0, then, well, it's just the linear DE, then it's trivial. Right? So if r is 0, then the D is linear. R always equal to 0, the D is linear. dy over dx, and let's put that in a standard linear form, plus qx times y equals minus px. This is a linear DE. Linear DE, so you can use the standard linear theory. You can use integrating factor, or you can use variational parameters. That's up to you. So I'm going to use integrating factor. Once again, this is very mechanical. You're unlikely to come up with such a method on the spot during the exam. So it's but this is standard ODE stuff. Integrating factor, let's write integrating factor as e to the integral of qx. This is how it works. Just memorize the formula. I know it sounds rather unmotivated, but if you want a more motivated solution, we can use method of variational parameter as well. So that's it. That is to say, we first solve the homogeneous case. You first solve the homogeneous ease, so basically artificially setting the right-hand side to be 0, and then solve the homogeneous equation using the method of separation of variables. In the solution, there's going to be an arbitrary constant of integration. Right? Method of variational parameter says you change that constant to an unknown function and substitute into the inhomogeneous DE, and you can get an expression for the unknown function. Okay, but that takes longer to write, so I'm just going to use the integrating factor. You multiply the integrating factor on both sides. This way, the left-hand side becomes a product rule. That's the purpose of the integrating factor. Okay, so on the left-hand side, after multiplying by the integrating factor, you get e to the integral of qx dx. By the way, I'm interested in how many of you guys have taken a course on ODE. Like just like say if you did or did not in chat. I'm just gauging like I mean, I haven't posed many ODE questions in quizzes yet. Do you want me to do that? Or just stick to calculus, real analysis, and linear algebra? And sometimes some channel related content like stochastic calculus? Because right now I'm not assuming background with ODE on the channel yet. Okay. So there's that. Anyway, so multiply integrating factor on both sides. It looks rather disgusting, but the left-hand side really is very nice. So that's a derivative of d over dx of the integrating factor times y. So that's what the integrating factor does for the linear ODE, at least. And now we can integrate on both sides. This looks ugly, but because this is general coefficient, so not much you can do about them. This would be like a derivation question, okay? But it seems to me that in North America, at least, there's not a whole lot of general derivation going on in exams. Instead, you're more likely to be given with specific P and Q. Just an observation. And then this way the exam can test you on integration techniques. For example, to solve this integrating factor, you got to use integration by part. Right? But here, not much progress can be set. Right? You can only keep the integrals as they are. Just an observation. I'm still watching. Yeah, hi, Vizzy. You still does this like does everything still make sense? You haven't taken okay. Yeah. So I mean a good resource ODE yet. Okay, haven't taken ODE. So a good resource on ODE. I mean, I'm trying to think of yeah. There's a free resource. There's a free resource on ODE which is amazing. Let me go find that for you. Similar to the open math that I just showed for linear algebra. It's called Paul's Online Note. This is an amazing resource for preparing for grad school and stuff and beyond, okay? This is really extremely, I would say, just top-notch content when it comes to basic calculus. So this, okay, what I was just talking about, the University of Waterloo Open Math is great for linear algebra. It's got video lectures, quizzes, and stuff. Although, I mean, not super comprehensive because as for linear algebra 2, the number of quizzes in the later part of the course became significantly lower. Okay, so do find yourself some extra practice. This is all lessons, not a lot of quizzes. In linear algebra 1, there's a lot of quizzes. But due to the format, there's a lot of calculation-based quizzes. For example, find a vector that's not in the span, blah, blah, blah. It's calculation-based, but it's not proof-based. I'm just trying to point out resources and their limitations. This is as good as free resources can get, in my opinion. Is your background more applied or pure? Applied. But I don't believe the distinction between pure and applied mathematics is something scientific. I've always tried to blur the difference, so to say, blur the boundary between applied and pure mathematics. I guess it's safe to say that as far as applied math channels are concerned on YouTube, mine are more proof heavy. Okay, because I don't want to give the impression that somehow applied math doesn't need proof, or applied math is not rigorous. It has its own rigor, and it has proved that it's no less demanding than pure math, in my opinion, and it requires modeling rigor as well. Okay? The distinction between pure and applied math is sociological, not scientific. There's no epsilon delta definition of. Let me take a note of this website. Yes, Paul Online note. It's got calc, basic algebra. I mean, you don't need that probably. Calc 1, calc 2, calc 3, and ODEs. Even PDEs too. There's some basic PDEs as well. Differential equations. You see, we were talking about separable equations, exact equations, and linear equations. Yeah, integrating factor is in here. We go to here, and it's completely interactive. You see, this is the form y prime equals f of y over x. This is a homogeneous form we're talking about. Substitution. So yes, this is an excellent resource. And it's completely free. If you want a text, the text by Edward and Penny is fantastic for first course in ODE. Okay. Hang on, let me go find that Edward and Penny. It's called Elementary Differential Equations with Boundary Value Problem. Let me, perhaps in the Discord server, I would put out my list of recommendations of all sorts of stuff. How's that sound? Yeah, this one right here. Damn, what's going on? Yeah, so basically, but if as far as free resource concerned, Paul's online notes is amazing. Go check that out yourself. It's got examples and solutions, and just amazing. And it's interactive. So this is the book. If you prefer a traditional book, this is the one I recommend for every beginner. It's ridiculously expensive. I mean, it's just unfortunate in the realm of academic publishing. What else can we do? Yeah, so amazing book, really amazing book. Hands-on, tons of examples, tons of exercises, lots of pictures. One of the best when it comes to intro to ODE. Okay. Let's continue. So yeah, why is this ugly looking thing? Purely because those coefficients aren't given. Yeah, I figured perhaps because my channel really got picked up by the algorithm because of the statistics stuff, right? The mathematical statistics stuff. As far as stats majors are concerned in North America, most aren't required to take ODEs. So that's why I'm not assuming ODE on the channel. But like I guess separation of variables can be assumed as a topic in calculus, which I put out, I guess, one quiz or something on the channel. But other than that, I'm not assuming extensive backgrounds in ODE. All right, so that's it. That's the first case, just the linear D. The y squared term gets killed. Okay. So part 5, once again, part 5, if you don't know, if you've never seen this, it's unlikely you would come up with a transformation. It's like if you know, you know. If you don't, you don't. Okay. Part 5 is called a Bernoulli DE. It's also in the Paul's online notes. It's also it's called a Bernoulli differential equation. Let's go. Part 5. You know, in Discord, you can Do voice chat once you make a server. Just paste the Discord link in the YouTube description. Yeah. 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 A lot of YouTubers do that. And I haven't figured out a way to let people post on my community tab. Do you guys think that's a good idea, or is that too messy? I see some channels do that because I want to like have people like talk to each other on the channel as well. Is that a good idea, or what do you guys think? But anyway, Discord server will be provided. All right, as soon as possible. And here we have. This is the Bernoulli D, what I was talking about. So this is nonlinear, right? Because of the y-squared term. The D is nonlinear. But fortunately, for Bernoulli D, you can always convert into a linear D. Okay, and then just use the integrating factor method we did earlier. Let's write out the general theory. Bernoulli D. The Bernoulli D has this form, y prime, okay, plus q of x times y equals, want to be a mathematical statistic course too, because I want to be a machine learning theory researcher. That's great. That's really awesome. So for machine learning theory, you would also probably need some optimization stuff. I'm just saying. Y to the n. Y to the n. Okay, let me just use this as a general format. Okay, r times r of x times y to the n. Okay, n is assumed to be non-zero and not 1. N can be fractional. Okay, it can be a general real exponent. Doesn't have to be strictly integers. But we do assume that it's not 0 and it's not 1. Because if it is 0, then it reduces to the previous case. If it is 1, well, it also becomes linear. So a Bernoulli D is taken as a nonlinear D. What's nice about this is that you can divide by y to the n on both sides. So this is, once again, one of those tricks that if you've seen it, then you know it. If you've never seen it, it's unlikely you would come up with that method in reasonable time. Because the thing is, the differential equation that has closed form solutions are so restrictive that you can list them with your fingers. Right, so, and now we're just going to do a change of variable. Let that be the new dependent variable u. U equals to y to the minus 1 plus 1. This way, by the chain rule, u prime is just minus n, y to the minus n times y prime. And see, wow, you got a y to the minus n times y prime. So that's a negative 1 over n u prime. Now once again, we see the importance of n not equal to 0, right? Otherwise this would not make sense. So now what we have, let's multiply by minus n on both sides. So you get u prime equals, u prime minus n q of x u equals n times rx. So this is a linear ODE for u of x. Linear ODE for u of x. So if you have linear ODE, you can use integrating factor. Okay, so that's the idea. Here is just the special case of n equals 2. I will not do this derivation again. Okay, so that's the general Bernoulli D. And a fun fact, is that the Bernoulli D was invented to solve problems in ballistics. Because if any of you guys read portions of Newton's Principia, the seminal work that settled the foundations of classical mechanics. In the second part of the Principia, there's extensive discussions on air drags or fluid drags, okay, fluid drags and its applications in ballistics. So Newton first figured out the correct form of air drag to a large extent, the quadratic air drag law. So basically the drag force is proportional to the speed of the object within certain limits, of course. And Newton was trying to figure out the solution to the differential equation of the projectile motion when the projectile is subject to the air drag as well as gravity. But the solution becomes too complicated that he couldn't solve it. So instead he settled down to some rather contrived cases in part 2, and some of them has mistakes in there. So it becomes an important problem and a challenging problem back in the 17th century to solve this projectile problem. So you have the force kv squared acting in the opposite direction and the gravity mg. So how do you solve the trajectory? And it turns out Bernoulli found a solution in that. And the key is the Bernoulli's equation. I was about to make a video on that. Perhaps I will someday, but right now I don't have time for it. Okay, it's a pretty interesting problem, and it explains the origin of this d. It's not just a trick for the sake of impressing some folks, I guess. It actually has very important applications, namely in ballistics. And Euler compiled ballistic tables. That's the range table for artillery, based on the solutions given by Bernoulli dE. Okay, basically Bernoulli dE reduces this ballistics problem into a bunch of integrals, which you can evaluate beforehand and make them into tables for the military. Okay, and that method was used all the way until World War II, at least for certain types of artillery. Okay, for artilleries with low muzzle speed, like the mortars, Euler's solution was used all the way until then. Okay, it's an analytic solution based on integration. Anyway, I digressed, because I couldn't help talking about a piece of mathematical history whenever possible. Anyway, let's go to the next part. In this case, as you can see, for the Riccardi equation, there are certain situations where we can have analytic solutions. But in general, this cannot. In general, if you have fully general PQ and R, then it's not reducible to an integral. Right? And but we can make some sort of progress. Okay, for the general case. And here is part 6. It says, if y1 of x is a particular solution of equation 2.2, show that equation 2.2 can be converted into an ODE in the same format in question 5, with a change of variable. Right, so this is good news. So if you know a solution of the original 2.2, then you can convert it into the special form that is Bernoulli. Okay, so that's the idea. So the key hinges on y1, having a y1, but it turns out that y1 is very difficult to find. Okay, so suppose we have y1 that solves 2.2. Suppose this is a given function. Then you can convert 2.2 into an ODE for z, where z has the form of part 5. All right. I mean, it's just an exercise in the chain rule, right? So that's not super exciting. But whoever come up with this transformation is genius. Me, I gotta go because there's a power out here. My phone is 2%. Sure, no problem. I'll keep going. Okay, I'll keep going for another 30 minutes. Thanks for staying with the stream. Okay, and I'll do some probability after that. Okay, I didn't know you gotta go this early, but anyway, you stayed long enough. I was about to do some probability stuff. Okay. Anyway, let's do part 6. Part 6. So suppose that you have a solution, y1, satisfies dy over dx plus p of x plus q of x plus r of x, q of x times y plus r of x y squared equals 0. Suppose you have that, and you have defined z of x to be y minus y1. Let's find the d for z. How about you take rest for the night? It's 10:30 now. It's too early for me to go to sleep, but I will stick a little bit longer. I'll stick around for a little bit longer. There's still folks watching. All right. Okay. So by now, busy. Thanks for giving me those problems. They're really fun to work with. And we'll finish up the linear algebra business for sure. Perhaps I'll make a video about polar decomposition. Find a d for z. And if I'm going to ever make linear algebra videos on this channel, because linear algebra is rather saturated on YouTube already, it's going to be a series called the linear algebras you missed. Okay, it's going to be topics that aren't typically covered, but still nevertheless pops up in applications and stuff, like tensors perhaps, and generalized inverse partition matrices in stats are quite important. Kronecker product, which is a special case of tensor product, as well as the polar decomposition we just saw, right? It's in Axler's book, but the courses on linear algebra rarely gets to that point. Anyway, find d for z. This is not very difficult, so you just write z equals, you just first express y as y1 plus z. So the left-hand side of the d becomes, dy1 dx plus dz dx plus px is unchanged plus qx times y, you get qx q of x times y1 plus q of x times z. Okay, and then r of x, expand the square, you get y1 squared. This is given, by the way. y1 is already assumed to have found. There's a power where that's the main issue. That's okay. That's okay. I mean, you can always watch the rest of the stream the next day when the recording is ready. Our x times 2y1 z plus what? Plus r of x times z squared, right? And let's combine what we already know. Because y1 is a solution, so dy1 over dx plus px plus q of x times y1, and then plus r of x y1 squared, this is 0. So these things sum up to 0. So you just get dz over dx plus q of x z, and then plus, actually we can combine the linear terms in z into q of x plus 2r of x times y1, and this is a completely known function in x, times z, and then plus r of x z squared. This is equal to 0. And this is in form part 5. So this is a Bernoulli DE, and do whatever you need to do. Okay. Okay, so that's done. And for the last part, we're going to do a concrete problem. Find the general solution. Find the general solution. Let's write down the DE first. Okay, so you have dy over dx plus p of x, that's x squared, plus x plus 1, plus q of x, which is 2 x plus 1 times y plus r1 y squared. So it's just plus y squared equals 0. So this is a fully general Ricardi equation. So this is a fully general Ricardi equation, and it turns out, and see if we can apply any of the previous technique we just used. Right, so that's the idea. So it appears from part 6 we need a y1. And y1 is not easily found, typically. You have to rely on inspections or specific tricks. So how can we find such y1 here? Is there anything special about this D that we can obtain a solution by inspection? That would be great. Right. So people on YouTube like to say, big if true. Right? Big if true. If you can find a y1, then the problem is solved, basically. So how do we figure out a special solution? You see, this is where I think the exam is not very fair. No, if let's say somebody just got super unlucky and cannot find a solution, and they know what to do next, and what they do, that's just they cannot write a single letter, right? Right. In North America, if this question is on the exam, they would give you a hint. Okay, what you should look for. I mean, maybe they just give you the y1 outright and then ask you to do calculation. But I guess, I mean, that's the reality of research, right? If you're getting into grad school, you sometimes do rely on luck. You know what? Why don't we just assume a polynomial solution? Why don't we just assume a polynomial solution? Because I can't figure out what y look like. Here you have p is a quadratic, right? And q is linear, and r is just constant. So can we assume that y is linear? Because if we assume y is linear, then dy dx is a constant. This part is quadratic. 2x plus 1 times y is quadratic, and y squared is quadratic. So everything has a chance of canceling out. Right? That's the idea. So let's try a special form, just purely based on the fact that p, q, and r has degree 2, 1, 0. Okay, and based on that, let's try, okay, no guarantee that this will work, but try y equals to mx plus b. Just a simple linear function. This way, you get dy over dx equals m plus x squared plus x plus 1 times 2x plus 1 times y. Okay, let's expand that here. 2x plus 1 times mx plus b. What do you get by expanding? You get 2mx squared plus 2bx plus mx and then plus b. Okay, so that's 2mx squared, 2b plus m quantity times x plus b, and then y squared. Y squared as well. Y squared, well, it's a nonlinear coefficient, but we'll see what we can do. M squared x squared plus 2mbx plus bx. So plus b squared. We want this to equal 0. So let's see if that can be done. Collecting the common terms, x squared has a coefficient of 1 plus 2m and then plus m squared. Okay? So these are the quadratics. And then plus linear terms, x, coefficient x, 1 plus 2b plus 1, plus m. And what other linear terms we have? We have 2mb. And what else? Constants. Constant, you got m plus 1 plus b and then plus b squared. So to make that an identity, we need quadratic term vanished, in which case m must be equal to minus 1. If m is minus 1, notice that how the linear coefficient automatically vanish for all b. If m is equal to 1, m equals -1, then it's 1 minus 1 plus 2b minus 2b. So this is true, equals 0 for all b. So that's good progress. And here you would have b equals what? B squared plus b equals 0. So b can be -1 or 1. B can be minus 1 or 0. Right? B is either 0 or 1. So that means y equals minus x or y equals minus x plus 1 are solutions. Let's check if this works. If y equals -1, the first term is -1. Okay, let's check. Okay, let's check. This is because I had this idea of using a linear. That is big if true, right? That's indeed big if true. So if we have y equals minus x, so it's got -1 plus x squared plus x plus 1 plus 2x plus 1 times minus x plus an x squared. Yeah, indeed everything cancels here. So this is true. And let's just take that to be our y1. Let's just take that to be our y1. And there's no need to show these in the actual answer sheet. You can just say, okay, by inspection, y equals minus x is a solution. Right? Feels kind of magical. But that was the original motivation, right? Because I noticed the degree pattern here. So I figure if I try y to be a linear solution, then this might work out. Right? Once again, this is pure luck. This is pure luck. I don't think the question is fair for an exam if no hint about how do you find y1 is given. Because that's way too random, right? Because I guess this is still, Japanese standardized test. So I don't know the exam culture there. Perhaps some emphasis was placed on ingenuity. All right, so you have y1, as we mentioned. Y1 is minus x, is a solution by inspection. Okay, let's complete the whole process in what? 4, 5, and 6. So to find the full solution, let's do that. So by our procedure in part 6, we would let z to be y minus y1, which is y plus x. Okay, so this way, y is z minus x, and then we substitute this into the dE. So the left-hand side of the dE would be dy over dx, which is dz over dx, minus 1 plus p, which is x squared plus x plus 1, and then plus 2x plus 1 times y, which is z minus x, and then plus y squared, which is z squared minus 2zx, and then plus x squared. All right, simplify. Minus 1 cancels out. X squared seems like cancels out as well. Yeah, it does. X squared just cancels out. And x cancels out. Because this is, if you expand that, you get 2x plus 1 times z minus 2x squared minus x. And we just mentioned that x squared completely cancels out. X does too. And what's also nice is that 2zx goes away. So you just get dz over dx plus z squared, right? So that's the left-hand side, and that's a very nice Bernoulli d. In fact, this is very similar to the logistic growth equation. Anyway, so let's finish this off. So dz over dx is plus z, use the Bernoulli method, okay? Plus z equals minus z squared. Divide z squared on both sides, you get minus z squared dz over dx plus z to the minus 1 equals minus 1. So we let u equals z to the minus 1. This way, du is minus z to the minus 2 z prime. This is du dx. Okay, so the first term is just du dx, and then plus u equals minus 1. Equals minus 1. So this, I mean, you can use integrating factor, but this is constant coefficient, so it's actually super easy to get the solution. I mean, because this is constant coefficient, du dx and u both has constant coefficient. Let's try a constant solution based on the formula on the right hand side. Because if you use a constant solution, u equals to k, big K, which we don't know yet, the derivative would vanish, and u, which is k, so k equals minus 1. K is minus 1. That's a special solution. K equals minus 1. That's a special solution, and the general solution should be the solution to the homogeneous problem. That is du dx plus v equals 0 plus this minus 1. So u is minus 1 plus the homogeneous solution just based on observing the left-hand side. That's a c times e to the minus x. Because e to the minus x add its own derivative equals 0. So that's the general solution of u. And now just a matter of work everything backward to figure out the original unknown y. All right. So u has found. Let's trace back. U is z to the minus 1. Therefore, z is 1 over minus 1 plus plus c e to the minus x. This is z. We have now z, then y is z minus x. So y is z minus x, and so it's 1 over minus 1 plus c e to the minus x, and then minus x. And that finishes off the problem. All right. So this is actually the first question, the full question that we managed to completely solve, the ODE problem. Right. Introductory ODE, like the one I've shown for the Paul's online notes, feels like a bag of tricks. Often feels like a bag of tricks. There's not like a unifying theme. Okay, but I guess it's just unfortunate that we have to solve specific Ds using specific methods. It's just the way it is, okay? But if you get into advanced ODEs actually have many unifying ideas. Advanced ODEs would require, let's say, show a solution exists and is unique, and you have other qualitative behaviors such as what does the solution behave near equilibria, those sort of stuff. So for introductory ODE, you gotta need to know many techniques. It's like if you know, you know. If you don't know, then it's unlikely you would be able to independently discover that yourself. Okay, it feels kind of magical, but once you get through that, ODE becomes very beautiful. Okay. Anyway, I digressed. Let's take a look at the probability question and see what we can do here. Anyone still watching? Hang on. Anyone still watching? Yeah. It feels like. How do you check how many people are watching in the stream? 14 people watching. That's crazy. 16. Okay, wow. So you guys were ready for some probability? Let's go. I think a lot of the new subs um, are from the the stats department, huh? Yeah, all of the new subs are from stats department. Oh hi, are you Korean? I can't pronounce your name. I see you posted a bunch of comments. Thank you very much. Thank you for your support. I don't know how do you pronounce your name, but I don't speak Korean. But thank you very much. And this is Japanese exam, by the way. Um, Japanese entrance exam for grad school. I like how the questions, it's very different from GRE, right? If you guys seen any North American like subject test GRE, they're all multiple choices, and they aim to cover a wide range of topics. But here we have just three big questions. Hi, please make more videos using geometry of statistics. I will. I will. Yeah, a lot of topics are coming up. I mean, the last geometric statistics video I did was Cramer-Raw lower bound. But there's still a lot of topics in estimation we haven't yet covered, like sufficient statistics and what's that, exponential family, and the geometry of likelihood ratio test. Those are amazing topics, and I barely see them mentioned in textbooks. So stay tuned for that. Yeah, the geometry of statistics. So very, in my opinion, underrated. And also there's the whole field of information geometry. You're treating, also if you're considering Olympiad, unfortunately no, because due to the general topic on this channel, I'm kind of targeting upper level undergrad and grad topics. If you guys notice that, right? Olympiad math is for, I guess you can have put in an exam for undergrad. That's like a competitive thing. But the channel mostly focused on applied mathematics. I don't want. It's possible. I'm not ruling out that entirely, but the focus right now is that it helps to build intuitions into, let's say, mathematical statistics, which is not usually a topic, in competitive exams, right? But it's difficult in its own right? It's got its own set of techniques and methods that's usually not very well covered in. What about differential geometry? Good question. Differential geometry, I mean, like manifold theory, or do you mean like differential geometries of curve and surfaces? Like manifold theory, yeah, we can do some of that, yeah, for sure. But I think it would be perhaps more realistic to have like a series on functions on several variables first, like a rigorous course on multivariable calculus. Because to discuss manifold theory intelligently, you got to know, for example, Michael Spivak's calculus on manifold pretty well, which is like a rigorous version of multivariable calculus, where instead of using vector calculus, you do differential forms. Those are like fundamental things, right? And also we need to cover things like tensors and stuff. So lots of stuff to cover, certainly. Differential geometry. I'm not a differential geometer, but I think I can say, like make an intro to differential geometry, like the basic manifold theory, so that would be cool. Like with an applied focus, okay? It's like, so people who wish to do things like classical mechanics and perhaps information geometry, but not for the sake of like proving theorems in differential geometry. It's more about getting the intuitions, right? It's kind of like the geometry of statistics I've been doing. I mean, there is an underlying theory of functional analysis going on in all of those videos, most of them, because we've been using like L2 spaces to visualize random variables as vectors. But there's values in a series of synopsis and history of inner subfield here. Yeah, that would be cool. There's just so many things to do on the channel, right? Because I'm not a historian of mathematics, to be honest. It sounds even better than applying to classical mechanics, right? That's the one of the major applications of manifold theory is the foundation of classical mechanics. Very cool stuff. And as far as I know, like introductory material on geometric classical mechanics are probably unheard of. Because here's the thing. For classical mechanics, there are two main types of literature, okay? First, you got the physics one. The best example is probably Goldstein. If you guys heard of Goldstein, but I will just show that real quick. That's like a standard grad introduction to classical mechanics. It's very much a physics text. Okay, so I can't show that here, but basically that's the book. So yeah, that's the book. The Classical Mechanics by Goldstein. This is very much a physics text. But there's a separate treatment, which is completely geometric. You work in something called the symplectic manifold. It's called a symplectic manifold, and that is given in a book called Mathematical Methods in Classical Mechanics by I think it's Arnold. Yeah, Vladimir Arnold. So mathematical methods of classical mechanics. So this is how mathematicians and physicists see the same subject from very different views. So that's the Arnold book, this one. They're roughly at the same level. I mean, this one and Goldstein are roughly on the same level. Okay, they're both quite dense works. But the thing is, in physics, there's usually a nice progression to Goldstein. In math, the jump is very high. Typically, to get into the geometric classical mechanics requires a lot of prerequisites. And it's not very easy, and it's not super intuitive. Yeah, and Abraham Marsden, my goodness, you mentioned that. Abraham Marsden is super dense. Abraham Marsden's The Foundation of Mechanics is very good. Yeah, it is very good. But, I mean, I'm not going to pretend that I understand everything in there or even like half. But, yeah, Abraham and Marsden is very, very good. That's like, I mean, in case you guys don't know, the rest of the guys don't know. I mean, we have a geometric mechanician in the chat. Yeah, if you mention Abraham Marsden, you know your stuff. So there we go. We have do we have that somewhere here? No. Abraham Marsden. What does that look like? It's a very thick book, as far as I can remember. And unfortunately, I think Marsden passed away not too long ago. So yeah, but Marsden's work are very good. Foundational Mechanics. And also they have this book right here. Hang on, where's that? It's called Manifold Tensor Analysis and Applications. Perhaps we'll follow that book by Abraham and Marsden. It's the same author, but specifically tailored for applied math. How about that? And I don't think you need to know like Spivak to follow it. You just need to know advanced calculus and linear algebra. That's the idea, at least. I haven't worked through it completely though. I walked through the first two chapters, which I think is pretty good. Where the hell can I open this up? Okay, there you go. So this is the one. Manifold tensor analysis applications. It's, I would say, upper undergrad and grad level, and it does not assume extensive backgrounds, but you do need to be comfortable with working in real analysis proof, so to say. Yeah, there's that differential geometry. But once again, these are aspirations. I'm not promising I can do that in near future, because right now I got the stochastic calculus series, and I'll see how well that goes. And the complex analysis videos are coming up next week, so I have a lot on my plate, and also the stat stuff. So it's hard to be like a whole department. Let's be honest here. Okay. Anyway, so where were we? It's already 11, but I guess I can stay a little bit longer. Let's do a little bit probability. Enough chit chatting. Let's do the probability problems. It says consider a moving point on a number line. The initial position of the moving point is 0. At each step, the moving point moves by 1, either in the positive or negative direction. So that's a random walk, each with probability 1/2. That's a random walk. For a positive integer n, denote Pn the position. My goodness, why do you use Pn? Okay, anyway, let's follow that, because P is already extremely overloaded in probability, but let's just follow that. Why don't we just use Xn? Anyway, sure. Pn is the position of the moving point in the line after n steps. It is assumed that the movements of the moving points are independent. Okay, this is a classic symmetric random walk. For a random variable x, let Ex and Vx be the expected value and the variance of x, respectively. Okay, so this is just the notations for expectation, variance, and probability. And we need to find the expected value of Pn, the variance of Pn, and find various bonds, I guess. Okay. Okay, so this should be, I wouldn't call it easy, but this should be a classic model, right? The standard random walk. Let's do that. Let's do the first three. The choice of problems are very interesting, as far as I'm concerned, it seems to me, because in North America, it's unlikely that a stat major would have taken, say, it's not expected at least to have stat major to have taken an ODE class, or an applied math major to have good backgrounds in probability. Right? So that's kind of different tracks. Here, the specializations are kind of, split early in the university career. You have very detailed programs: pure math, applied math, combinatorics, and optimization, stats, computer science, mathematical finance has its own major. So people kind of just do their own thing. But what is this book again? Oh, I don't know anything about random walk, but probability theory is kind of okay. What book is this? This is not a book. This is a Japanese grad school entrance booklet. It's submitted by a viewer, Vizzy, who has now left the stream. But this is a very good set of questions, and it's only got 2.5 hours to complete. right? It's only got 2.5 hours to complete. I mean, I did spend a lot of time explaining my thought process. So maybe if I'm doing it independently, I'll be able to doing it faster. But let's not sugarcoating things because I struggle with the first question, the linear algebra one. Oh, this is Japanese. But anyway, I did had a hard time with part two, the uniqueness, and part three. I didn't even have time to look at part two and three of part three. So yeah, this is not an easy exam. And we just finished part two, problem two entirely, and now we're at problem three. Okay. Anyway, so let's start with the random walk. So it's a classic random walk, symmetric, which by the way is intricately linked to the Brownian motion we've been doing on this channel. The Brownian motion is a continuous limit of sort of the classic symmetric random walk, in which the step size in time and space satisfy a very special scaling law as those sizes tend to zero. Right? So that's a very long sentence. So basically, the Brownian motion is the limit of this process we're seeing on the screen right now. It's a limit of the symmetric random walk. Thanks, many thanks, and deeply grateful for your sessions. Please continue a dedicated, beautiful session for students across the globe. Thank you very much for your support. Yeah, so find the expected value of Pn. We can write Pn as a sum of random variables, independent random variables, and apply, I guess, central limit theorem and stuff. So each step, you either go left or right. So let's denote xn the displacement of step step n. Okay, so xn is 1. Let's with probability 1/2. That's right. The probability of xn equals 1 equals the probability of xm minus 1. So somebody asked earlier if I'm going to do like Olympia stuff, like competitive math. It's unlikely. It's unlikely because it's unlikely, at least in the near future, because the focus of the channel is to what does the channel tagline say? It's called Mathematics with Applications. Enjoy. And the channel banner says bringing math to life, right? So it's got this heavy, I mean, even though we do things like the fundamentals and proof and stuff, it's always built towards some sort of applications, right? Those things are rarely, if at all, a concern in competitive math, right? So because there's a lot of physicists, engineers, and statisticians, data scientists on the channel, and they have their own priorities, right? So they're not typically interested in solving difficult math problems for its own sake. So that's why it's unlikely for me to get into the Putnam stuff. I mean, you like if you're interested, well, you can check out Michael Penn. Like, I mean, it's a fantastic channel. I learned a lot of abstract algebra from that channel. Michael Penn. He's been making math videos way earlier than I ever did. So there's that. But basically no Olympia stuff. This is not a K-12 channel, first of all, and it's not very much focused on the competitive scene. So here we have let's write PR. That's the notation for probability given the question. So Pn, where did it start from? It starts from 0, no? Yeah, it starts from 0. So Pn is the sum of xi, I from 1 to n. It's the sum of all the displacement. Find the expected value of Pn. Expected value of Pn, just use linearity, is the sum of the expected value of xi, but because of xi is symmetric, they're all 0. Part 2. Find the variance. Well, because xi are independent, the variance of Pn, the variance of Pn is the sum of the variance. And this is, as we shown on the channel, a Pythagorean relation. The sum of the variance equals the variance of the sum hinges on the fact that the terms being summed are uncorrelated. That's an orthogonality relation. So this is essentially a Pythagorean theorem. Okay, so the variance of xi's are what? Because mean is 0, more books for self-study scholars, for sure. I really should compile a list of stuff, a list of book recommendations on my Discord, on my soon-to-be-made Discord. Okay, because I get these sort of questions all the time. What do you recommend for X? What do you recommend for Y? And I found myself answering those questions many times. And I would like to hear like other people's thoughts as well, because I learn a lot of good books. I learn about a lot of good books from just comments. Yeah, it's amazing. The variance of xi is the expected value of xi squared here, because the mean is 0. exi is 0. And xi squared is always 1, because xi is either 1 or minus 1, right? So xi squared is always 1. So the expected value of x squared is just 1. So that's just the sum of 1. Therefore, it's just n. The variance grows linearly in time. Yeah. 3. Show that for any positive integer k, the probability of satisfying Pn greater than k satisfies the following. And this is a general statement about probability. Okay, it has nothing to do with random walk. This is true for this is true. Yeah, this is true for any random variable with finite variance. So 3, this is the Chebyshev's inequality. This is the Chebyshev's inequality, okay? Chebyshev's inequality. Or if you're Russian, it's pronounced as Chebyshov inequality. Okay, so why don't we just give an exposition of the Chebyshev's inequality and then apply to this problem. So to discuss Chebyshev's inequality, we first need to discuss Markov's inequality, which recently I asked a question in my post about Markov's inequality. So the statement of the Markov inequality says, if random variable x is greater or equal to 0, then for any a greater than 0, the probability, let's use the notation PR, following the notation recommendation in the question. PR of x greater than a, greater or equal to a, is less than or equal to ex over a. And I asked the question in my community post that whether this inequality can take equality. Right. So there's a whole bunch of proof of this inequality. Now there's a whole bunch of proof, for sure. But I would like to just give one proof, okay? I will make a separate video on Markov inequality, but let's today just give one proof. for random variable greater or equal to x, its expectation, for non-negative random variables, I mean, for non-negative random variables, its expectation has this identity. The expected value, this is a theorem, by the way. The theorem says if x is greater or equal to 0, then the expected value of x can be written as the integral from 0 to infinity, the probability of x greater or equal to little x dx. It's the integration of the tail probability. Okay, you have this theorem. Let's prove that. We can assume, you don't have to, but let's keep the discussion elementary. Let's assume that x is continuous. Let little f to be the density of x. Then the right hand side, the integral from 0 to infinity, even though this is, we're just verifying this, okay? We're not giving enough motivation because I wish to get to the Chebyshev inequality sooner. The right hand side of this integral, the right hand side of this equation is the integral from 0 to infinity, probability of x greater or equal to little x dx. So we can express the tail probability as an integral itself, and then just interchange the order of integration. That's it. So what's this? This is the density of x from x to infinity, f of y dy. Right, so that's the tail probability. Probability of x greater or equal to little x. And then dx. So that's the integral. And let's plot the region of integration. How do we plot this, this region of integration? Well, it looks like x is greater or equal to, x is greater than 0, and y is greater than x. X is greater than 0, y is greater than x, so the region is this sector. X is greater than 0, y is greater than x. And x, and by the way, here x is a non-negative random variable, so the density equals 0 on the negative x-axis anyway. So the integration only cares about this particular sector here. Right, so this is the only region we care about. That's the region of integration of this double integral. And then we just change the order of integration. By changing the order of integration, we mean you would have dx, dy in this order. So that means you're fixing y and then figuring out the values of the range for x, right? So y can go from 0 to infinity. Y can go from 0 to infinity, and what? And when y is fixed, when fixed y is just a standard exercise in Calc 3. If you fix y in this region, then x must go from 0 to y. So from 0 to y like so. Okay, and because the integration inside has nothing to do with x, you can just write it as 0 to infinity y f of y dy. But look, this is just the definition of the expectation. So this is e of x. And that's proved. This is change of order of integration. But here we prove it for the continuous random variables. You can replace the integrals by sums and make that work for discrete random variables. And in fact, those are also special cases. This property has nothing to do with the nature of the random variables being discrete or continuous. This is true for all non-negative random variables. And it has a beautiful interpretation, which I'll make it in a separate video, so stay tuned for that. And why does this have to do with Markov inequality? Well, with this identity in mind, the Markov inequality is a simple geometric relation. Let's see how. So we have the identity first, Markov inequality second. Okay. The identity says the expected value is the area under the curve of the tail probability. Let's recall what the tail probability looked like. Tail probability is the complement of the CDF, right? This is 1 minus the probability of x less than or equal to x. Once again, I'm assuming continuous random variables. Okay? So the CDF would look like this. X is non-negative random variable, so it goes from 0 to 1 as x goes from 0 to infinity. So this is a CDF, and 1 minus the CDF is a decreasing function. It tends to 0. This is a tail probability. This is a tail probability. So the theorem says the expected value is the total area under the tail probability. That the area is Ex. So we have that. Let's draw a bigger picture. So that's the CDF, not the CDF, but the tail probability. This is the probability of x greater or equal to little x. It's a decreasing function. It doesn't have to be strictly decreasing. I don't know why I click on this video since I'm still taking high school geometry. Oh, welcome. I'm sure, I hope some things I say will make sense to you. Hi, James. Yeah, I got like 10% of my followers are high schoolers. I made a poll on the channel. You guys can go check that out to see what bracket you sit in. Most of the subs are undergrads. Anyway, so this is the tail probability of the random variable x. It's a decreasing function from because x is non-negative, it decreases from 0 from 1 to 0 as x goes from 0 to infinity. Okay, so it's a decreasing function. And the total area underneath, as we just mentioned, is the expected value. That's the average. So the average can be interpreted as an area. That's Ex. So that's the area here. Okay, so imagine if we pick an arbitrary positive number a, right, and the point on the curve would have height probability of x greater or equal to a. And let's look at this this rectangle here. This is the rectangle. The rectangle would have area probability of x greater or equal to a times a. That's the area of the rectangle. And of course, this is no greater than the total area under the curve. So this is less than or equal to Ex. And guess what? That's the Markov inequality. Okay, explained using high school geometry, sort of, if you know this identity. So that's the Markov inequality. And now you can just apply Markov inequality to all sorts of non-negative random variables and get better bounds. This is very crude. Right? This is very crude. So I posted a question in my community tab whether this inequality can attain equality, whether Markov inequality is sharp. So what is the condition for equality? Well, the condition for equality from the picture is obvious. Basically, the tail probability curve needs to be a rectangle. So it has to be like a step function. It's a one-step function. It steps from 1 to 0. So when equality happens, the tail probability function would look like this. It's obvious from the picture. So A is here. And the probability dips from 1 to 0 at the point A. And this is a decreasing function. So, but what does this mean for the random variable? it means the random variable can only take, hang on, this is not right, this is not 1. It doesn't have to be 1, okay? In that case, that's a deterministic random variable. It doesn't have to be deterministic. My apologies. So it dips from 1, okay, to p. It dips from 1 to p, yeah, let's say some height at the point A. And then it dips to 0 at precisely the point A. So this way the area under the probability, the tail probability curve is the area of a rectangle. So the construction for such x based on this diagram would be x can only take two values, either 0 or A. So if you're taking a basic probability class, you would know the jump position of a discrete random variable. If you, let's say, first of all, if you have a step function as the CDF or a step function as the tail probability, that means the random variable is discrete. And the values it takes are the jump discontinuities, the location of the jumps. So it's a piecewise constant function. So here x can only equal to A and 0 with positive probability. So x equals A with probability P, and x equals 0 with probability 1 minus P. So these are the only two possibilities. Okay, and let's take a look at the probability of x greater or equal to A. Well, x greater or equal to A is the same as x equals A, because x can only take these two values with non-zero probabilities. But this is just P, right? Because this is just P. But hold on, what's the expected value here? What's the expected value of x based on this definition? Well, this is just 0 times 1 minus P plus A times P. So this is just AP. So AP can be written as EX, so P can be written as EX over A. And look, Markov inequality attains equality for this only, for this situation only. So this is how you answer the question whether Markov inequality can attain equality, and how do you get there. All right. So Markov inequality now is explained. So we can use the Markov inequality to get all sorts of bonds. Right? This is a rather crude bond, but things can be improved. For example, the next improvement is the Chebyshev's inequality. Chebyshev's inequality is used for proving the weak law of large numbers. Okay, so now let x be a random variable. It doesn't have to be non-negative anymore, with finite mean and variance. Finite mean mu and variance. Basically L2 random variables. Okay, so what does the Chebyshev inequality say? It says the probability of x minus mu absolute value greater than or equal to k times sigma is less than or equal to 1 over k squared. Okay, for all k positive. So this tells us the chance of a random variable deviate from its mean by k times its own standard deviation. And that is bounded by this factor, 1 over k squared. Okay? And the proof is very easy. Because we can take, because the, let's write it this way, since x minus mu squared is a non-negative random variable, right? You can apply the Markov inequality to this random variable, okay? Not to x itself, but to x minus mu squared, okay? The left-hand side, x minus mu absolute value greater or equal to k sigma. This is the same as the probability of x minus mu quantity squared greater or equal to k squared sigma squared. These are equivalent events. And by the Markov inequality, this is less than or equal to, but x minus mu squared is a non-negative random variable, so you have expected value of x minus mu quantity squared over k squared sigma squared. But guess what's on top? That's the definition of the variance. So you, sigma squared cancels, you get 1 over k squared, QED. That's the Chebyshev's inequality. So let's apply the Chebyshev's inequality to random walk, part 3. So Pn, we know that Pn is has mean 0, right? So Pn absolute value is just Pn minus its own mean. And here we have greater or equal to k. Well, we have greater or equal to k. What's the... Okay, by the Chebyshev's inequality, back to 3. By the Chebyshev's inequality, the probability of Pn minus 0, right? 0 is its own mean, greater or equal to k times the variance of the standard deviation. The standard deviation of Pn. The standard deviation of Pn is what? Is the square root of n. Is less than or equal to 1 over k squared. Right? This is less than or equal to 1 over k squared. So what do we want to show here? We want to show this k squared. Okay, so let's write this as t. Let's replace k by t. Doesn't matter. Okay, so write, let's write k to be t times the square root of n. So the probability of Pn absolute value greater or equal to k is less than or equal to, let's multiply the right hand side by both the top and bottom of the right hand side by n. So n over t squared n. That is n over n, which is the variance of Pn. Variance of Pn, and now bottom is k squared. And that's what we wanted. So if you know Chebyshev is just one step. Right. So I took the opportunity to go back to from Markov to Chebyshev. Okay. So that's part 3. Anyway, let's go back to the question sheet. Have 4 parts to go. But part 4 is trivial. Part 4 is just Markov applied to this bond right here. And now, so this is another bond, by the way. Another bond based on Markov known as Chernoff. This is a Chernoff bond. This is a Chernoff bond. So let me just walk through that real quick. Once again, this should be well known, but I'm not sure like what the Japanese curriculum is like. So basically, we started from Markov, right? And we got Chebyshev. So to get Chebyshev, we just need to take the non-negative random variable in Markov inequality to be x minus mu squared, which is obviously a non-negative random variable. But you can use other non-negative random variables. In Markov, you can use, for example, an exponential function, right? Because for any random variable x, no matter its sign, e to the tx is always greater or equal to 0. And what would be the advantage in doing that? Remember, when we apply the Markov inequality here, in Chebyshev's case, we get a quadratic bond, right? Or a quadratic bond, a bond in the deviation probability that is quadratic to the times that the deviation is of the standard deviation, if that makes sense. So this decays according to 1 over k squared, which is not very fast. It's a pretty conservative estimate. So if you want to wish to have a sharper bond, you would want the random variables in x to grow faster than quadratic. So that's why we take the exponential to try our luck. Okay, so but you do need to have the expected value of the random variable, the expectation of the random variable, not the expected, the exponential of the random variable to have a finite mean. So that's the thing. Okay, so let's just do that. This is essentially the Chernow bond. I don't have the precise statement of the Chernow bond in my head right now, but this is, you can look up, called the Chernow bond. So the first step, this is a one-to-one transformation. The exponential function is a one-to-one transformation, right? So e to the tx is increasing. This is increasing in x for t positive. So these two inequalities are equivalent events. Right. So that's it. And this inequality is Markov. So that's it. So question 4 is done. The question 4 is done. And now part 5, we want e to the tpn to have this bond here. You have this bond here. How can we do that? Well, we have the, for part 5, right? For part 5, the expectation of e to the tpn is what? Is the expectation of e to the x1 all the way to xn. x1 all the way to xn were our steps at each movement. Right? Pn is the sum of xi. And because these are independent, you can factor the expectation and simply get e to the expectation of e to the tx1. And by the way, this is called the moment generating function. This is the MGF. Chat, have you seen MGF in like anywhere? This is the MGF. MGFs are useful for a bunch of stuff. You can use the MGFs to calculate the moments. You can use MGF to show independence. You can use MGFs to characterize distributions. And here we see an application. You can use the MGF to give a tail bond. That's cool. Anyway, here, but we need the expectation for each of the txi. But that should be easy, because Saw it all the time in statistical mechanics book. Yeah, in statistical mechanics, really. That's cool. I saw MGFs are only used in probability. In statistical mechanics, they use something like it's called a partition function, isn't it? In statistical mechanics, the big Z, the normalization condition in the Boltzmann's distribution, big Z. And you perhaps take the log of the partition function called it's called the cumulant generating function or something. It's been a while since um, I did any statistical mechanics. Fun subject though, very fun. A lot of followers of the stochastic calculus series were interested in non-equilibrium statistical mechanics. So I figured, right now we did the Ito's lemma, right? You can see financial applications to, and we'll get to Black-Scholes, and after that will be a more physical treatment. So I initially decided to cover like the math, like the core math of stochastic calculus. Energy is second cumulus, so MGF is. I see. That's cool. So I was thinking for a stochastic calculus series, I'll do the fundamental math, but I figured it's not good for views. um, it's not good for views because right now at Ito's lemma, the views are already dipping. If we go too deep into the theoretical math, people lose track of where it actually matters. And just to be fair, it's hard to keep up with the upload, right? So I figured might as well heat capacity is second cumulant. Oh, actually, I have no idea. Perhaps I forgot. Probably forgot. Anyway, it's very rusty. This is the thing about math and physics. Like you have to, I mean, you have to, let's say, practice to such a degree that it completely internalized, or you just forget them. I mean, one of the courses I took was statistical mechanics. But it's hard in retrospect to say I fully internalize of what's going on. I just mostly just apply the formulas and do the exam questions. And I mean, sometimes you have to do that. It's unfortunate, but unless you try to internalize it, then those things atrophy. Yeah, unfortunately, that's the case for statistical mechanics for me. I would love to pick it up one day. It is very deep. Anyway, back to the question. What do we have here? This is the MGF of m of xi of t raised to n. But what is m of xi? M of xi, well, because xi only has two values. M of xit, by definition, it only has two values. Right? Xi is either 1 or minus 1. So it's either e to the t or e to the minus t over 2. But here this is something different from what we want. Expected value of Tn squared. So how do we get that? Here we have, I mean, we just expressed the expectation of T Pn exactly here. How do we have that? We need to get a T squared. This is the exact MGF. We just found the exact MGF. And by the way, this is cos, hyperbolic cosine of T. So this is the exact MGF. That's the exact left-hand side. So how do we get the bond on the right-hand side? Let's write it this way. So this is e to the natural log of the cosh. The natural log of the cosh of t, right? Standard trick, and exponential, and then times n. So compare with our goal, we just need to show that the natural log of the cosh is less than or equal to half t squared. So what we need is this simple relation between the natural log of the hyperbolic cosh and half t squared. So this is what we want. So this is just a regular calculus problem. And here's the thing, right? And here's the thing. So we can, I guess, do a series expansion. Do a series expansion on the left or something like that. So let f of t to be the natural log of the cosh. And I think, yeah, sorry, the Korean fellow. You've probably seen a lot of this stuff, the natural log of the cosh in statistical mechanics too. That's as far as I remember, but I can't name the specific application now. So I wanted to do a Taylor expansion in that. So can we, an exact Taylor expansion with a remainder term. So this is obviously an odd function. Sorry, obviously an even function. So let's calculate the first few derivatives. F prime of t is 1 over the cosh times the cosh derivative, which is sinh. So f prime at 0 is 0. The second order derivative is, by the way, this is tanh. So tanh has a derivative of sech. So f double prime at 0 is 1. Third order derivative obviously 0, but we need the expression. That's the same. And the fourth. So, because it's kind of getting late, I'm just going to use a calculator to find that. So I'm going to use a calculator to find the derivative of sech. The derivative of sech is negative tanh times sech. So third order derivative is 0, as expected. And I need the fourth derivative. The fourth derivative is sech the fourth derivative is sech of t times the tanh of t times the tanh of t minus the sech cubed of t. Right. So what I'm doing here is I'm going to do a third order Taylor expansion of f of t. So this way, the three terms are, actually the four terms are, the constant term is 0. If you plug in t equals 0, you get 0 here. The first order derivative is 0, so the linear term is 0. The quadratic term is half t squared. And the third order term is 0. And then you would have the remainder term, which according to the Lagrange remainder theorem is the first order derivative evaluated at c over 4 factorial, okay, and then times t to the 4, where c is greater than 0 or less than t absolute value. Okay, so that's the remainder form. But now let's look at f4's derivative. Is this positive or negative? Oh, actually, there's a tangent square. So this is, the fourth derivative can be simplified as sech. Sech is always positive. Sech is the reciprocal of cosh. Cosh is positive. And then you have tang minus sech squared. So which one is bigger? Is tang squared bigger or sech squared bigger? Right? So that's the question. So this shouldn't be too difficult to find out. I think sech should be better. This is strictly less than 0. Tang is strictly less than sech. So the remainder is negative. Okay. Here's a picture of hyperbolic functions. Let me try to find that. Sech. I'm looking at the Wikipedia page here. Right, this is a Wikipedia. So do we have an identity that links sech and there should be an identity that links sech and tang. So tang by definition is tang by definition is sinh over cosh, and sech is 1 over cosh. Hang on. Hang on. This might not be always the case, no? Tang is less than cosh or not really? Because I want to make sure the first order derivative is tang squared minus sech squared. Is it always positive? Or is it always negative? I think it's always negative, but I'm not quite sure. Or is there a better way to do this question? How do we get the t-squared bond here? How do we get the t-squared bond? Or maybe just, can we expand the exponentials directly? Because that's easier than working with hyperbolic functions, no? No, not quite. I still need the e. That's the thing. I still need the e. If I expand at this step, then e would be destroyed. Tang squared minus sech squared. Or, bro, this is too complicated. Let's do just a simple calc 1 proof. It's not very smart, but gets the job done. Let phi of t be the natural log of cosh, because I'm getting tired. Let's just wrap this up real quick. Minus half t squared. F prime is, as we mentioned, the sinh over cos, which is tanh, minus t. So this is tanh minus t. So obviously 0 is a critical point. But what's the nature of the critical point? Right. So let's take the second order derivative to find out. So this is tanh has a graph that looks like this. Okay. Which is tangent to y equals x or t. Okay. This is tanh. So this is negative when t is, actually you don't need the second derivative because you just need the monotonicity. Is less than 0 if t is positive. Actually, and we only care about t positive. So this is just less than 0. And that means f prime is negative or t positive. So f prime is negative. Therefore, f of t is less than or equal to f of 0 for t positive. So this is to say f of t so this is to say the natural log of the cos of t minus half t squared is less than or equal to f of 0. F of 0 is just 0. So we're done. As needed. Okay, so it just boils down to this simple calculus problem, and therefore e of t pn, t to the pn, is less than or equal to e to the half t squared n, and we're done. So there's a mini calculus problem in between. Compare the natural log of cos and half t squared. All right, so that's part 5. We're done with this part. And now we're just going to use this bond for the expected value. So that's the bond for the MGF, right? So and use that for the Chernow bond in part 4. Use it in part 4. P of the probability of Pn. Is it probability of Pn greater or equal to K? Yeah, sure. Is less than or equal to this bond right here, e to the half of t squared n over the bottom is e to the tk. Is e to the tk. So simplify, you get e to the half t squared n minus tk. Okay, so we want this. But the thing is, this is true for all t. This is true for all t, so we can consider minimize this function. So therefore, because this is true for all t, therefore, the probability of Pn greater or equal to k must be less than or equal to the infimum. I'm writing infimum, not minimum, because we don't know if the minimum exists, but infimum must exist. Right? Because this function is greater or equal to 0, is bounded below. By the least upper bound principle from real analysis, if something is bounded below, its infimum must exist. So it is less than or equal to the infimum of the right-hand side over, when the infimum is taken over t positive. Right? So therefore, you just need to minimize the exponent. E to the infimum of this quadratic function here. This is a quadratic function in t. And what's that? Let's draw a picture. I assume k is positive, no? In the question, does it say k positive? Yeah, positive integer k, so k is positive. So the quadratic function, half t squared minus tk, has two roots. Has a root 2k over here and a 0 here. This is a quadratic function. Half t squared. It concaves up and has two roots. So it must look like this. So the minimum is obvious. It's just when t equals k. When t equals k, simplify, you get e to the half k squared minus k squared. So that's e to the minus half k squared. Is that what we needed? Oh, I forgot the n. I was dumb. So the 0 is now, we cancel out the t, you get 2k over n. 2k over n. You now plug in t equals k over n. So t squared is k squared over n squared times n. So it's the n here, t times k times k over n. Yeah, so that's what we wanted. E to the minus k squared over 2n. The minus e to the minus k squared over 2n. Yeah, that's exactly what we wanted. So yeah, you just minimize the upper bound in part 4. You just minimize the upper bound over t, because this is true for all t. And that's exactly the idea of a Chernoff bond. You use the MGF to create a bond and minimize over t. Pretty ingenious, actually. So now I guess you just use the bond for part 6 and apply it to part 7. But here we needed the bond for absolute value, no? Absolute value, so this is not exactly the same as, but I guess you can say Pn is symmetric. Yeah, Pn is symmetric, so this still works. 7, we want the probability of Pn absolute value to be greater or equal to 10 to the 6. We want that. This is 2 times the probability of Pn is symmetric, greater or equal to 10 to the power of 6. Right here, and n is 10 to the 10,000. Here n is equal to 10 to the 10,000. So first, let's apply the bond we found in part 6. This is 2 times what? 2 times e to the minus k squared over 2n. What is k? K is 10 to the 6, right? So that's 10 to the 12 over 2n. And n is 10 to the 10. So here we got 2 times e to the minus, you have 10 to the 12 over 10 to the 10, you just get 100. 100 over 2. 100 over 2 is 50. Okay, now just use the calculator to figure out this number. Hopefully it's less than 10 to the minus 4. So 50, so how do you do exponential? I don't use this calculator very often. E raised to the power of minus 50, I suppose. That's how it works. My goodness, I'm so bad. I can't use a freaking calculator, man. E to the power of 50. This is already much smaller. This is way smaller. Even times 2 does almost nothing. Right, so this is way smaller than 10 to the minus 4. Right, so that's it. So that's the probability question done. So we're able to figure out the entirety of the probability question, which is fortunate, I would say. We didn't quite have the time to finish up the linear algebra part, but it is what it is. Okay, so this is part 6 and part 7. All right. Anybody still watching? This is getting way too long. I streamed for like 5 hours and 10 minutes right now. Anyway, so I think I'm going to call it a day because it's right now in Canada 12:10, which is a lot. Okay, so I'm going to turn off the stream now. If you have any questions, you can just comment anywhere on the channel, any of my videos, community tab, or when the stream recording come out. Any questions other than the Discord thing? I am. Hi, John Doe. Good content. Thank you so much. Hopefully this is helpful. Anyway, yeah, I really need to redo the Axler's book. It feels like because I got my ass beaten with the linear algebra part. Have a good night. Thank you.